for being online too. So today is the first day of LaFusion. This is a tutorial day. LaFusion is a preparatory event for the Fusion conference that will be in Rio next year on July 7th to 11th. So this event is divided in 2 days, tutorial and paper day. Today we have 4 courses. We have a small change in the schedule. Instead of having like introductory data fusion course, at the first moment, we have data fusion for time machine learning. We will invert the first and the last tutorial. And my name is Claudio Micelli from the Federal University of Rio de Janeiro. And this is Paulo Costa from George Mason University. We are both from ISIF, International Society of Information Fusion. And we are delighted to share this event with you.
So, good morning, everyone. Thanks for coming. So today is November 28th. That's the second workshop, as Claudio mentioned, and for us it's a pleasure to this for the second time, and hopefully we'll be organizing for more. It is we have as sponsors here the International Society of Information Fusion and the Federal University of Rio de Janeiro, so we are very thankful for them for supporting us. As Claudio mentioned, this is like a prep event to the larger conference that will happen in July. July 7th to July 10th. It will be in the Autumn Palace, Copacabana Beach, here in Rio de Janeiro. So we hope to see you all there. It's a very nice event, large conference with all the features that you expect from one of them. And here we will have this workshop divided into 2 days, which is an improvement with respect to the first version, where we just have the presentation of papers. This first day, as Claudio mentioned, we'll have the tutorials, 4 of them. Tomorrow, we'll have panels, presentations, and it will be also in the Fusion venue, which is the Autumn Palace Hotel. So without further ado, I would just like to introduce our first speaker, which is Professor Claudio, who will be talking about data fusion in TinyML. Thank you very much, Claudio.
Just another mention, we are also supported by the Latinx in AI organization. It's a non-profit organization that tries to give scholarships and support for Latin American people that's already working on AI. So although AI is not the main topic of data fusion is the main topic. It's not the main topic in Fusion. A lot of the new techniques involve AI, so we are trying to do this right now. So it's with me now. Let's go. So this tutorial, it's enhanced version of the tutorial that we have seen in Fusion this year. So it's okay. So, as Paulo mentioned, my name is Claudio Micelli. I'm from the Federal University of Rio de Janeiro. I am from the graduate program in Computer Science and Engineering, the PESC, from COPI, and from the Test-to-Pacit Institute of Applied and Computational Research. I'm delighted to be here. I've been professor from the Federal University of Rio de Janeiro for the last 10 years almost, and it's a pleasure to be with you. So this tutorial was given this year in Fusion 2024. This is an enhanced and minimized version. This was a 3-hour tutorial during Fusion. So we have covered the most important aspects of the conference. So let's go. So my main point is that's one of the first things that I think is important to notice, and I always state this, is we are on an AI revolution. This is seen. This is heard. This is noted. But the most important thing that you have to notice about this AI revolution is it's mainly a data-based revolution. We can't do AI properly without doing data. So where does this data come from? Nowadays, it comes from the web. So that's noticeable. And mostly this not only from the web, but smartphone web. We have to understand that most of the data nowadays is mobile data. Data that comes from cell phones, from smart bands, from tablets, computers are not the majority of the web nowadays. But we are about to change it. We are starting an IoT revolution. The IoT movement talks about interconnecting devices into the web without human intervention. It's different from when you have a cell phone with you and you send a message on WhatsApp, you send a message on a file chat, or you send a message on Slack or whatever, because you intentionally sending data. You decide to send a message. This is something that you decide to do. IoT is different because it's non-decide. There is no decision about sending data. The data occurs based on an event. And for you to take into consideration, how many IoT devices do you believe there are today on activity? How many? Give a guess. 10 million. 50 million. More, less? More, how much? 1 billion? Billion, 1 billion? 10 billion, how much? We have an estimate with the Siemens. We have done a work with Siemens. The keynote for tomorrow will be from Siemens. In this work that we're working on, we have an estimate that nowadays we have around 65 billion IoT devices. But the projections last to 2035 to 1.5 trillion devices. We are working on one, and if you go to 1.5 trillion devices, in less than 10 years, the web won't be human anymore. We have an estimate that 70% of all web data will be IoT data. So this data that gathers information about the environment, about temperature, about positioning, about telemetry, about all these things, will be the most important thing on the web. And this is important because this is the data that will fuel the AI revolution, not us. ChatGPT is great. ChatGPT is awesome. But it's for humans. Not good enough. So this IoT revolution started when I started working with this, like almost 15 years ago. It passed through phases. The first phase is a data collection phase. So we had a network like the first one here, where you have a sync node, some nodes, and you send data from the nodes to a computer, and that was it. That was the point. So that's the problem, because each network was dependent for one application. So if you're monitoring like fire detection, you have a network for fire detection. It's good. It's worth it. Actually, most of the products nowadays still work like this. You get information from a sensor to go to a server, and the server do all the computation problem. So this doesn't work like the internet. The internet doesn't work like this. The internet is composed of several thousands of applications running simultaneously in a given infrastructure. So it led us to the second phase of IoT network, called the shared sensor network phase, where I had a single infrastructure shared, where multiple applications share this infrastructure. For instance, if I have like a air conditioning application and a fire detection application, I don't need to collect temperature twice. There's no need for that. So I can collect this data once and bring this for a lot of other applications. It's very similar to what we do nowadays to microservices approaches. So there is a lot of similarities between them. And as it grows around 2014, 2015, we went to the virtual cloud. What is the IoT cloud? What does it mean? That we have like a three-layered architecture. And most of the IoT architectures will work on this three-layered approach. We'll call it differently, but we have a sensor tier, a layer where you get the data, an edge layer, a layer close to the sensor, but not as powerful as a cloud service, and a cloud layer where I have a lot of computational data, but too far from the event. That's the idea. So we have a three-layered architecture where you can exchange data between them. So the problem right now is, where do I take decisions? Because at the first phase, I was taking a decision just at the edge. We were not talking about clouds. And then we decide to go to the cloud, too far from the event. But there are some events, there are some decisions that cannot be taken too far from the monitored event. For instance, if you're having a heart attack, you don't want this thing to go to AWS to take a decision, unless you don't like the person. But that's not something that we're going to try. And this is a very, very Christian seminar. So we don't try to kill people here. And so then the problem becomes the restrictions that you have. This is an optimization problem that you have to try. So where do I take the decision? How many resources? How much do I need to do before this is a problem? So this decision, this scheduling becomes a problem. So where do I place those algorithms? Where do I place this data? So, and that led to what we call Industry 4.0. Industry 4.0 is one of the most interesting revolutions that we are passing right now. It's not the idea that we replace sensors, cyber-physical systems, and those things will be held accountable, and you just collect the data and take decisions about factories. What? Oh, okay, thank you. The idea is that this arose between 2011 and 2013, and the idea was not about collecting data from the sensor to take decisions. The main idea was simply try to map all the society process into industrial processes. If I could use this AI and use this IoT data to monitor process, I could try to predict problems in my production. For instance, if I'm trying to produce a shirt, I can try to see if my cotton production, it's enough for the number of shirts I have that I want to produce. If the number of trucks, it's enough. If I have hours in the factory, they are enough. Or if I have some problem to the production, I can try to reduce those things on real time. And this is something very important because it reduces the cost, reduces the environmental impact, and it's still leveraged for profit, but still not good enough because it still relies on mass production. So we came to the Industry 5.0 paradigm. What this paradigm means, it's not a fifth industrial revolution because we can't have an industrial revolution every 5 years. So if you have, it's not a revolution. It's just an ongoing process. The idea is that since now I have the cyber-physical systems data, could I use this and AI to predict your needs? So I could, instead of do mass production, do real-time mass customization of human processes through what we call cyber-physical cognitive systems. The AI means cognition, means that I can understand, predict, and produce things for you on real time. We are talking about additive manufacturing. So I can produce, if I want a t-shirt, for instance, I'm a computer science guy. For me to buy a computer is a nightmare. I have to buy a new cell phone. My cell phone is broken, and I've been trying to choose a cell phone for the last month because no phone has everything that I need. And no computer is exactly what I want it to be. It sometimes has less RAM, sometimes it's not thin enough, sometimes the layer is not metal, and I end up not buying anything at all. So if I could produce this on real time, if I could see, say the specs, and the factory can adjust to produce anything that I require on real time, and without enhancing the cost. This has a big impact on sustainability because I don't need to rely on mass production. It's human-centric because it takes into consideration my personal needs. And it's resilient because I only take the resources that I require. So it's an optimization problem. It's a software engineering problem. It's a mechanization problem. And this leads us what we call a digital transformation. This is the moment we are passing right now. We are going through the Industry 4.0. Very cool, very interesting name. What we're trying to do right now, the moment that we are, is a digital transformation where the needs of networking, don't get me wrong, AI is great. But if you don't have fast networks, there's no AI for that. We need AI, and AI is a great tool. But we need not machine learning only. We need general AI. We need probabilistic robotics. We need mapping. We need localization. We need automation processes. We need those robots to be working for us. We need Internet of Things. We need to collect this data and be able to clean it. We need data. We need to be able to process this data, we need communication. This is something that not only comes from technology, but we need to enhance our communication paradigms. For this to work, we need to trust everyone in the process. And this communication leads to blockchain in a lot of scenarios, because those guys that are in a production process, they don't trust themselves. They don't trust each other. They shouldn't. Why should they? So how can we enhance clear communication and trustworthy communication? We need these advancements in technology to be able to host these elements. And that's our point, because these things commit mistakes. This is a famous case in Brazil. This I took from YouTube. It was a famous journal in Brazil. And this guy, he's a software engineer from IBM, a data scientist that graduated from PUC. PUC is a prestigious university in Brazil. For those who do not know, he was in jail for, I think, 22 days because some machine learning system, some face recognition system recognized him as a thief. And of course, the machine learning system is wrong, committed a false positive, but no one fixed the problem. So this leads to that problem of digital transformation that we had. That led us to a big issue. It's not supposed to fix us or to replace us, but to enhance us. So this is not only a machine learning problem. This is a human problem. This is a process problem that you have to recognize. And some books have been working on this, discussing this problem for the last 20 years. This book from Shoshana Zuboff, The Age of Surveillance Capitalism, is a book. Shoshana Zuboff, if I'm not mistaken, she's a social researcher from Harvard. She wrote this 1,200-page book, an amazing social analysis about technology, and it's a book written from people from social analysis. So the fact that I read this book, you can interpret it as an act of love, because it's really a difficult book to read, really tough. It's not our language, but the discussion is deep and powerful about the problems that this data led us to take. And this Weapons of Math Destruction from Carrie O'Neill has an amazing TED Talk. This book is from 2013 and talks about the problems of big data not well done, or data that doesn't use a trustworthy statistics, and the fact that most of those systems are black boxes. And we don't know what is deciding about us. And the biggest problem that this book brings us is simple. That poor people will be judged by systems, and rich people will be judged by people. And this is a huge problem in our society. It's a technological divide. There's a very important book, and this book is from 2013. We were not talking about AI 10 years ago, not like this. So this problem is an ongoing problem, so we can't ignore this. And if for us to understand the time that we are right now, my personal belief, we are not in general artificial intelligence, as people is saying around. So we're still an artificial narrow intelligence. Most of the products that we have nowadays are artificial narrow intelligence products. We are going to artificial general intelligence. Until I see the papers, until I see the data, I'm very skeptical. I don't trust them enough to see that's general intelligence, because we have problems on the definition of intelligence, big problems in the definition of mathematical definition of intelligence, mathematical definition of consciousness, in the mathematical definition of what is learning. And for instance, what we do nowadays, most of the machine learning, artificial intelligence we are talking about is machine learning. And I hope that you haven't learned to cross a street by error and trial. Not good enough. We learn by rules. Your mother said, look at both sides of the street, then you cross. You don't keep trying. That's not how we learn. It's good for machines. And data does not cover all cases. Data does not cover all cases. So to reach here, I personally believe there's still a lot of things to do, but this is good enough for a lot of complex problems. Where do we use machine learning? When it's difficult to find rules, where it's difficult to map stuff with the data we have. So what do we need to reach this point where machine learning is useful in a scenario when I have 1.5 trillion devices? If those 1.5 trillion devices can now decide about your life, can decide if you're having a heart attack, if you have sugar on your blood, if you should run, if you should exercise, if you should sleep more, if the work's a problem for you, if you should decide those things, you would not want those things to be reliable, at least at some point. So what do we need to reach there? We need software engineering. So one of the things that when I started computer science, so not so many years ago, is that the disciplines, the courses, the topics, the areas were very apart. If you are from software engineering, you are a very software engineering guy. If you're machine learning, AI, you are a very mathematical guy. If you were from computer networks, you were a very probabilistic guy. And those things were divided. Nowadays, it's not like this. Can't be like this because those things are products right now. So we need ways to develop applications. If you're using machine learning applications to this embedded scenario, to take decisions, I need software architectures to build those applications. We need context-aware development models. We need to understand that these models, they change given the environment and given the person. What means being healthy is different from person to person. It's different. What is a way, for instance, a problem that we have nowadays, like to measure if someone is fat or not. What does it mean? It changes from people to people. How can I adapt to this? How can I adapt what's a healthy temperature? For instance, in Rio, 19 degrees is cold as hell. It's a very hard winter. If you go to Portugal, it's a spring breeze. It's amazing. If you go to Finland, it's a good day. For us, it's hell on earth. But if you go to 40 degrees summer in Rio, it's average. It's okay. It's not uncommon. If you go to 40 degrees in Northern Europe, it's something that they are not prepared of. So how can we adapt our systems to scenarios that change, to scenarios that might be on movement because you are on movement right now? And how can those applications do? And those applications must integrate themselves. What does it mean? One of the first problems that I worked on my PhD was what at first I thought was a very simple problem. I have to work with fire detection and air conditioning. So let's imagine those applications have their own rules and very simple rules. If there is a fire, temperature goes up, and then CO2 goes up. Those are the distinctions. And that's okay. Seems a very reasonable fire detection system. And if you have air conditioning, if you go up from 23, you go down. If you are below 23, you go up, and that's pretty good. So if I take a sheet of paper and here I put fire, put some lighter on this, it will start to increase the temperature. This is the normal thing. First, increase temperature, then CO2 detection is up. But if I increase temperature in here and the air conditioner is on, the increased temperature, the air conditioner say, okay, it's heating, so I go low. Perfect, okay? This masks the application behavior. So in a very simple application such as this, you have a masking problem. How can we deal with this in more complex scenarios? And Claudio, but this is a very simple case. This is an exception. Most applications are independent, kind of. But we're working on the smart grid scenario about electrical grid. And when you're talking about independent electrical networks, we have to have batteries. If you're going to rely on multiple electrical grids, you're relying on renewable energy, if you're going to rely on other sources of energy, these sources are not reliable, they are not constant. Those sources are based on the availability of resource, availability of sun, availability of wind. So we have to have batteries. And we had this system that we were a partnership with Metro some years ago that had a battery and a overhead power line transmission, what we call Iron Man. So we use a California data set to base our simulations. And as it passes energy, goes through the battery and through the line. So this battery works like a no break for cities. Cloud is like 15 minutes no break. No, it's a millisecond no break for it to turn on a power generator or something like this. It's okay, it's very powerful, very interesting. But one of the things that work like this is, what does it happen with energy? Energy is not 100% stored. You have a percentage that becomes heat. And if the battery is heated enough, it explodes. I have a beautiful little scar in my arm because my experiment was not well performed, and I learned the hard way that you should be careful with real experimentation scenarios. And there are ways to do this. You have to cut the energy production. You spend the energy from the battery, try to maximize those stuff. And we have this data, this heat expansion data that we get from California. It does not work on Rio. California is dry, here is very humid. What happens with heat in humid scenarios? It stays on the air. So we created like a microwave aspect around the battery. It does not happen in California. This is a problem. And this is an example of application integration. The battery monitoring and the overhead power line monitoring, they monitor the same type of variable, but one application affects each other. And those problems are not systematic. Claude, but I can solve this. Apple solved it. No, Apple didn't solve anything. Apple created their own ecosystem. They say, if you do everything Apple, it's okay. If you do everything Google, it's okay. If you do everything Microsoft, it's okay. If you try to mix those things, it's pretty far from okay. It's pretty a miserable experience most often. Try to use Google Calendar and iCalendar and try to mix stuff. It gets weird very fast. So how can we do this in a scenario? It's not sane to believe that there will be a single company that will take care of all those stuff. And how do we manage the knowledge about the scenarios that we are learning on real time? You can't do this. Some environmental conditions are unique to some countries. And how do we produce software for those countries? How can we trust the interactions between the data from different applications? Imagine that you have a milk factory. So you get milk from the cows, you transport on trucks, and you go to a factory to produce butter, to produce ice cream, whatever. The guy who produced the milk wants to say that he produced 500 liters a day. That the guy that transported the milk will say that he transported 550. And the guy that received will say that you had received 400. Who should I trust? And another problem about this thing is, this guy is malicious or it was an honest mistake. My measurement capability is good enough. And in my very short answer is not at all. We had this problem with the milk line of production, and the guy that measured the milk inside of a truck, he used a broom as a ruler. You place the milk on the truck, he picked up like a broomstick, placed on the milk and said, okay, you have 200 liters. And this is a billionaire business. Milk production in Brazil is a billionaire business, and they measure milk using a broom. I won't say the factory, but it's one of the big milk producers in Brazil. You buy their milk on the supermarket every week. They are billionaire business and they measure like this. If the billionaire business are measuring like this, imagine the other guys. That's a big problem. And since we're producing software, how can I do CI/CD in an environment that is changing every time, that the machine learning, the data sets are changing every time, that the hardware is changing every time? We are not working with something that uses x86 architecture. We are going on something that not only uses ARM architecture, because 10 years ago, every computer was quite similar. The processor is faster or slower, more RAM, less RAM. Nowadays, we have different types of architectures. We have like Apple machines, we have ARM machines, we have tablets, we have cell phones, but in IoT, we are not even using ARM. Yeah, we usually are using whatever. We are even producing our own processors with their own data sets. And how can I learn without exchanging data? Because now data is a personal and valuable asset. So those are the challenges that we are working on my lab right now. So we produce some architectures throughout the years. We'll pass very fast among this. This is Asgard was one of the first architectures that we have been working on. And it has been a lot of changes about what we should do. Like we should monitor. So this monitoring part has data fusion on it. I have to take this data and I have to clean it in some way. And there's several forms of cleaning the monitored data. We have filters, we have machine learning, we have good old averages, and those things work. We have scheduling tasks. We have to, those multiple applications, how can I schedule multiple applications in a scenario that is totally distributed and divided? How can I decide inside of a sensor? This is a problem. I have limited memory, I have limited processing power, I have limited everything, I have to give a fast decision. And how can I go to have distributed decisions when I have those millions of devices? When I see some papers that take like 15 sensors to take decisions, okay, 15 sensors is okay. They are semi-natural, they are within reach of each other. But when I have 1.5 trillion, I have millions, I have tens of millions, I have tens of thousands sensors, this becomes some other thing. I was into the industrial IoT forum from Petrobras last year, and they were discussing the proof of concept from Petrobras is 150,000 sensors. They are very good on this POCs, this proof of concepts. But the real scenario has some millions of sensors. And they are not being able to work on IoT with millions of sensors. So you still have a gap. And that's one of the problems between industry and academia. We can't understand this gap because we don't have access to this kind of problem. We don't have millions of sensors. In my lab, I think we can host like 2,000, 3,000 sensors at a time. And if I coordinate with other labs, you can reach 100,000 sensors. We have some test beds on this, but doesn't go to the scale that those major companies need. We can't solve the problem without knowing that there is a problem. And when you got to this point, you say that's Internet of Things, how I make those things reach Internet and say that it is really a first-class citizen of web. He has 1K of RAM. I have 1 megabyte of RAM in the great scenarios. How can I say that it's like a computer? And nonetheless, we have been seeing in the last few years some IoT attacks. One of the most interesting on the sociological aspect, okay, interesting on the security researcher aspect, I've seen a denial of service attack last 2 months ago, made by toothbrushes that had systems, electronic toothbrushes that had breached on their security system that was used to produce a denial of service attack. It was pretty successful attack. So now your toothbrush is an enemy that you should take care of. Now, the Dentistry Association won't like this. But we have I remember like 1 year ago, an attack that was to a hospital that came from a coffee machine. So things are getting pretty weird about the things that they do. And if you take this into consideration, if you think that like a smart vacuum maps your home, things get pretty nasty very fast. Imagine that you have a smart band on your wrist, and now it's measuring your heart beating, and someone can try to say if you are telling a lie, or if you are nervous, or if you have, I don't know, some health problem. Imagine that now I'm a company that gets your personal data, personal health data, to increase the value of your health insurance plan. I don't need to get data from your email. I can get your heart data. And that's a bad thing. That's a very bad thing. So traditional sensors don't send data. That's where we come from. But if they only send data, I can't send the data. Claudio, this makes no sense at all. Now, of course, I'll explain. Data relies on batteries. So sending data is expensive. So what we do nowadays, we discard most of the data. We use algorithms, filters to discard most of the data. And this data is not necessarily bad data. It's sometimes good data. So what do we do? So the on-device intelligence, the only solution. And people on data fusion has been doing this for the last 10 years before AI. But what do we do now? So use machine learning is usually centralized too. We rely on collecting data, go to a big server, lots of RAM, lots of processing power, and going to do those things. And there's a lot of power required for the data transmission. There's a lot of processing power required. One of the major flaws that we have in machine learning nowadays is that we say that we have an energy problem before we have a processing problem. We don't have energy enough to power those things. Microsoft reopened like a nuclear power plant just to try to fill the void of energy that they have. So those things are not suited for sensors. They rely on AA batteries sometimes. So it's not that simple, actually. So we're going to the embedded machine learning world. This, Paulo, can you control time? Okay. The embedded machine learning world, it's pretty exciting environment that started in 2019 from the Time Machine Learning Foundation. The TinyML book, it's a very good book, but it's not an updated book. It's a very interesting book from Pete Varden. And Pete Varden was one of the main minds behind TensorFlow. TensorFlow, the open source framework from Google. And Pete Varden made the TensorFlow Lite Micro. It's a reduced size TensorFlow running on sensors. This is an Arduino sensor. It costs $20 on the Arduino website. This is a Cortex M0. This is an ARM processor dedicated to run AI algorithms. Costs $20 on Arduino website. On bulk size prediction, this may cost less than $1. This is an ASP-I. This is an ASP32 that has a camera embedded. This is a sensor that do computer vision. There are computer vision algorithms running on those things. Face recognition inside of a sensor. This Spark fund only exists to enhance the power of those sensors. It's a complex, interesting, and this book is easily available through a lot of venues, and it's a very cheap book. There's a lot of videos on this, and this is not a new thing. So what changes from traditional machine learning to time machine learning? We go from process, after the training we have to do distillation, quantization, and encoding. What does it mean? It means that after getting data, I will have to work on this thing inside of the sensor to analyze the data and train the model and then compress the model. And how do I do this? The first thing that we do is to prepare data that we were going to call quantization. What does this mean? We are not working with 64-bit processors. We are working like we were in the 80s. So most of the algorithms that I don't get from new books. I go to the old books on the library. Yes, those still exist. So we still get those old books, and I try to redo the algorithm that we use in the 80s to produce data. Because if you try to stop to think about it, sensors nowadays are pretty similar to computers in the 80s. They use similar architectures, 8-bit, 16-bit architectures. They have similar amounts of RAM, 64K to 1 megabyte. And they have the similar data word. So the 8-bit data words. What we're trying to do is to summarize it. So instead of minus 33, I go to minus 34. Instead of minus 18, I go to minus 19. So what we do about this is to reduce the data sizes and rely that by having several or hundreds or thousands of sensors doing those kinds of calculations, the sum of results it's as good or better than a single network. And surprisingly, it does work. It does work pretty well. So the other thing that we do is I don't try to understand everything with a single sensor. I distribute my intelligence into several small pieces of problem in a process called distillation. Those distillation problems means that I'll have a pre-trained model in a big environment, and now train the devices into smaller models called student models that will be trained inside of an embedded device. So I had a student model that is quantized. This is so reduced that works pretty well. And after training those models, I cut the synapses that doesn't work very well. They are not important. So I cover all the aspects of learning by amount, not by using these techniques. So, and if I want to do even better, my quantization technique won't be a direct summarization. I use machine learning. I use data fusion to produce the quantized data. I would data fusion. I use like filter techniques, like such a Kalman filter, to predict what will be the next step of the layer. So I can give you a better result, a result that will be really, really fast. So it's not a new problem. It's not something that we've been doing for the last 10 years. We've been working on this for the last 30 years, but now I have place to work on. And who is talking about it? It's not only me, it's not only my group, it's Google, it's ARM, Microtransfer, STM, Samsung. And I was in ICML this year, International Conference on Machine Learning, to present a paper. And on their ICML, Meta showed their version of my TensorFlow Lite Micro, their PyTorch Micro Lite or vector search. That's pretty impressive. So a lot of people is working on this because people understand in the next 10 years the IoT revolution will be a thing. And it's pretty easy to work on those things. I use very traditional operating system, but the main core is Zephyr. Zephyr is a project from GNU Foundation. It's the Linux from embedded devices. And STM is also amazing. They have a lot of platforms, but Zephyr is superior in everything. I think it's when I started working with embedded devices, everything was pretty complicated to work on. You have to work with FPGA, C++, and I still work with C++. I'm not a Rust guy. I'm still working on C and C++ more often than nothing. But Zephyr is great. Zephyr is like next approach. It works on Linux, works on macOS, works on Windows, works better on Linux, okay? And then you have to install an application called West. West is just an application configuration approach. You start your embedded project by West in its Zephyr app, configure the project as a project conf file, write the code on C++ or even Python. There's approach like MicroPython that I show in the last few minutes. You build to a given board and flash the board, and all the layers of the stack, all the network protocols, all the scheduling managers are already implemented to you. And everything that you have to do is to work on the application, so it's pretty fast. It becomes a package that's so good, so fast to work on, that we have no issue to work. And if you don't have the sensors, we use emulation. Renode, it's an emulation platform from Renode.io that works on the hardware that you are working on. They have the platforms that you are working on and leverage you to have each of these screens represent one of the sensors, the emulation of one sensor. And if you have like 32 gigabytes of RAM, you can reach up to 150 sensors. If you have a good enough server, you can do whatever you want, because it does not only emulate the hardware, emulate the networking capabilities. So this is like a virtual machine for each sensor. And if you're not convinced that you can still use CI/CD like GitHub Actions to work on the code of your sensor, so you can produce a pipeline that produces a network with some lines of code on the web. And this becomes a game changer for people that are producing solutions, because you can now test millions or billions of devices if you have enough processing power. We can produce a massive network and try to summarize data delays, communication losses without leaving your computer, without requiring the hardware at first. So yesterday we had the TechNav conference, and one of the questions is how can you test those embedded applications in real time? Use typical CI/CD through emulation first. Before being able to be on a sensor, we have a long way to produce data. And this is pretty fast, pretty amazing, actually. And we use very traditional boards, especially S32, Raspberry Pi Pico, that you can buy on any online market for like $2, $3, even less sometimes. A lot of this Arduino Nano BLE you produce using Platform.io. This is a free software plugin. Use VS Code if you want to. I use VI for most of the things, but I'm weird. So it's you can use everything that you have been already using, and it becomes as fast as working on a web platform. We have to learn one thing or two, but come on, you still have to learn one thing or two. So if you do not work on this, we still can still work embedding on edge. So if you have some applications that actually require some more power, you can use platform as edge impulse to collect data from the sensors and do some wedge training and try to make the distillation on a web service. So this is serverless embedded programming. We can do your own computation on a serverless base and still have your data inside of your sensor. So, and it's as easy as get a collab. If you don't want to work on this on your computer, you can use a collab and generate a sensor image for you in a web browser. Cheap and extremely fast. This is the collab. Is not Cloud. You produced this. I didn't produce anything. This is from Google. This is the first example from Google, because they understand that this is a big problem. So, and you feel, Claudio, but I don't like C. I don't like Rust. I worked on C on the 80s, on the 90s. I don't like C. For you, C is amazing, but you can still work on Python. You came from machine learning, you don't like C, you want to work Python. There's MicroPython. MicroPython is an MIT-based, if I'm not mistaken, software that is a subset of Python 3 to work on sensors. You don't want to work with C? Great. You can use machine learning in Python inside of your sensor. And with several in our libraries already implemented, several IT protocols, you have plugins for VS Code, they have their own IDE, PyCraft, and lots of simulators, and it's good enough to fit in 16K of RAM. So you can get your Raspberry Pi Pico that you bought by $2 and place Python and just import MicroPython. Claude, but it's not fast enough. Then you code in assembly, because there's an ASM assembler inside of MicroPython that you can call the board directly. So Cloud is not interpreted. No, they use a more intelligent approach. They use like a direct interaction with the hardware. So we can take a look. This is a simulator on the web. You can go to the MicroPython website. There you give an ARM emulation inside that you can try code. And they have their own board, Pi board, and they have the low Pi, that's a board that has Slaughter 1 embedded. I would show some code examples, but I think we are running out of time. And we are working right now, several of my students are here today working federated learning. Now, instead of exchanging data, that I know that's something that is very valuable, that is very personal, instead of exchanging data, The federated learning approach is a set of algorithms run that started on Google in 2016. And the main idea is, instead of sharing data, I will share hyperparameters of my machine learning model. So my sensors collect data, they will train this data, produce those distilled models inside of the sensors, and they will exchange those models between them and sum those models in some way. There's several techniques to sum those models, and a lot of my students are working on different ways to summarize those models, and then you try to update on a server. So the idea is that the server will have a global vision, but each of the devices will have a local vision. If the global vision is better than the local vision, I'll just exchange the parameters. And this is much faster. This is much better than exchange all the data or collecting all the model itself. I can have what we call horizontal federated learning, where I get a single feature with a lot of data, or I can get vertical federated learning, where I get a lot of features, but a small amount of samples of each of them. So the idea that this whole process is encrypted, so I can't see your data, I can't see your hyperparameters, unless I am working on this with you, or I can use blockchain. There's a lot of blockchain federated learning models going on right now. We're going to present our way of doing the blockchain federated learning, the Multiset conference in 3 weeks, I guess. I think 17th of December will be my last conference of the year. And unfortunately, it's an online conference for me, but it is what it is. So, and the idea that you have a secure exchange of only hyperparameters, it's a way that ensure that your personal data is not shared. There are problems about this, because you can't say, if I have your hyperparameters, I can try to produce synthetically your data. It is true, but we have to work on this. So there are several types of federated learning systems working on different machine learning models, not only neural networks. You can use linear models, k-means, random forests, of course, neural networks. We have the federation can be cross-device or cross-ceiling. I can have the model that's from a region instead of a single sensor. I can have different privacy mechanisms. One of the things that we are working right now is in homomorphic encryption. This is a very nice strength work inside of sensors. And how do I make people work with these things? Because do I want to share my data? Do I want to share my hyperparameters? How I can incentivize this? I can do this by regulations. Is either you share or you pay a fee, or if you have sharing your data with me, for instance, in a car, in a car scenario, if smart cars with a vehicle network, I can try to do this, and in exchange for reduction in taxes. So those things are important for us to them. And in this scenario, these sensors, they can learn from things and exchange data with each of them. And this is interesting, because now, how can I do this transfer learning? By just exchanging hyperparameters. And this is powerful, and this is pretty fast. And I have, of course, problems. How do I do with stragglers? What do I do with nodes that lost battery? How can I work with these things? So I have some challenges. I have the statistical heterogeneity. If I have different sensors, they may have different architectures that understand data differently. They have problems in training data. They have a heterogeneous hardware. I have limited memory. So I have still working on this. And we have options like asynchronous federated learning, like data injection. And what we have done in our lab is to create the ways to represent this data through functions. This was the master's the word dissertation of one of my students called Gabriel Caldas. He's not here. He's doing the professor examination on the other side of the street. So I'm really proud. 2 of my students are doing this test right now. So they are not here because of this. And the idea is that instead of represent a mass of data by the data itself, I can collect statistical aspects of this data. And this is really reduced. So I can represent a mass of thousands of data by its average, by its standard deviation, by this kurtosis, by its asymmetry, and through this multimodality way of data, if assuming that I can go to a Gaussian in some ways, I can generate a function that will synthetically represent the data much better than the data itself could represent, because this data is faulty. So if I can clean this data as I receive this data on real time, I can produce a function that is more reliable to the phenomena than the data itself. What does it mean? It means simply, I don't give a damn if the temperature of the fire is 59.7 or 59.8. What I care is there fire or not? If you think this as a data fusion approach, I'm going from the data to a symbol on real time. So I'm represent this, and this has an advantage. Instead of storing a lot of data on my sensor, I can store average, mean, standard deviation, kurtosis, asymmetry, and the next data. So every time I receive a data, do a computation and just update this value. And this is a very powerful result. So a lot of this work in the basis that this data is asymmetric by nature, and I will have to do some distinctions, some adjustments in real time, and this leads us to knowledge fusion. Knowledge fusion is a concept that came also from Google, but 2014, from Xin Luna Dong. And Xin has a very interesting career because she was in Google in 2014. Then she went to Amazon in 2016. Then now she's on Meta because of this. The idea is pretty simple. Data comes from different sources. They have different formats, but I don't care about data. I care about meaning. So this came from the web, because she said, like, in the web I have HTML files, I have XML files, I have TXT files, I have images. How can I extract knowledge from them and create a single database? And actually, this is the thing that we wanted to do. I don't want to know the temperature or the CO2 concentration of the data. I want to understand that there is a fire. So how can I do knowledge fusion? How can I connect this data to different systems and in the internet to my smart grids, to my water management, to my resource efficient management? So what we're trying to do is to go to try to tackle this interesting approach in a resource constrained approach. So what we're trying to do is to map how those coexisting applications can access a situation. How can I have a less contradictory and redundant decision? And the approach that we do is a probabilistic approach. We try to create a knowledge model that's called action I implies in action J, and that's a factor O. And we will improve this using subjective logic in the next moment. So we produce Tina. Tina is from the other Gabriel that's also doing the tests on the other side of the street. So I want to collect data I use in the paper from Athena, a math and move every filter to work on this, but it could be any data fusion procedure. And by the technique that I use here, this local decision, I want to exchange with the possible outcomes. If the outcome is negative, I increase the cost. If the outcome is positive, then I reduce the cost. So I'm giving to if you take a decision that is correct, I will value you. If you take a bad decision, I will increase your cost to say something. And this is a very Bayesian network way of doing stuff, but it's pretty simple and pretty fast for a sensor. So we apply this for that problem that I told you about the smart grid environment, and the result is pretty low on resources and with great results. You see, in the very complex scenario, the traditional techniques, even traditional machine learning techniques, would be worse than flipping a coin. We have almost 20% of increase in the result. So
Bayesian is a very good technique.
Bayes still work. It's amazing, no? So and to further work on this, we started from subjective logic. Subjective logic, I learned about subjective logic from another guy from the Fusion Conference 2016 with Aldon Yozung. Aldon Yozung will be our tutorial chair next year, so we have a chance to know him. Subjective logic is extension of the traditional logic to work what's called subjective opinion, where I have not only an uncertainty about the data that I collect, but I have an uncertainty about the environment that I'm collecting data. This data, what I work is what we call a subjective opinion. So I have to create ways of trusting those sensors. Imagine that now I'm taking to a decision, and you have this guy in, for those that like me are Botafogo, great day for everyone. It's an amazing day. No? If you did not understand, you're not Brazilian. But trust me, it's a good thing. And the idea is like, if someone says something like Botafogo is going to be the champion of this year, you have a level of trust on these people. But someone says, it's not because he supports some other team, you can't trust his opinion enough. Someone comes from abroad that doesn't care about Brazilian football, says, okay, I'm seeing the scores, makes sense. He has a lot of chance. So this, what we call subjective opinion. I have indications that something is true given the environment and given a lot of people around it. I'm trying to find ways of trusting people on this environment. And we did this to work on this work, also a fusion paper on, I think, 2016, 2017 too. Working on this is one of ways of compression non-anomalous data. Because what we're trying to do now is, instead of representing the data that I already trust, that makes sense, I only want to represent the data that I don't trust. So I can summarize and compress data that it makes sense. For instance, there's 50 degrees, so it's a fire, makes sense. But I want only to showcase the data that doesn't make sense in the total environment, in the traditional environment. So instead of only do the quantization like we did, forming the function, I have the function plus the anomalous data. So now I can have a middle term to work on the data. So I can have this anomalous data is interesting for me. And after this, nowadays we're working very much with weightless neural networks. There are different type of neural network without weights. When I use the geographical position of data, like the topological position of data, to map decision systems. And we use the wizard architecture that we using one new technique from the wizard architecture called Beethoven, applied to computer vision to work on computer vision side of sensors. So last year we presented on the IEEE PyCon conference a paper about using weightless neural network on computer vision for edge AI. And we presented a type of network using this, since the computer vision has, if you are using like computer vision to map like Zoom calls that you want the face, but you want to try to tackle the background, this usually is expensive in terms of computing resources. And what we're trying to do is to use like really small boards, like Raspberry Pi boards, to try to tackle this result. And the result, if different scenarios, different activity scenarios, and the result was also pretty awesome. The result's pretty good. This is the loss curve. No, this is the loss, and this is the accuracy, and we are going having very good results. And the mapping says like I have an interest region. I can, instead of mapping those things in traditional wizard networks, those things are randomic. Instead of doing random mapping, we do what call a purpose mapping. I map the regions in the way to try to tackle the discrimination that masks what we're trying to do. What I'm trying to say is, I will place in several photos regions with change of colors like correspond to our face with one value. And I'll start comparing several photos. And the idea is, instead of to do like sigmoid functions, I do sum functions. I just keep summing. Oh, I trust you. Perfect. I would use this. I'll trust you. Okay, this pixel is good enough. I'll give you a okay sign. So if I do this enough, I can map the results, and this is a radar built using this approach. For those, this is the Jetson Nano board using a radar to rebuild in real time using Raspberry Pi, the Jetson Nano board. And you can see that's the Jetson Nano development kit. And this was done inside a Raspberry Pi. This is a different. This is a radar. You use computer vision technique to build a radar that can produce the box again. And we had very good results in precision regarding several activities in a very famous data set, and very effective for AGI. We want to test out different types of neural networks as classifiers. We have a group of people interested in this, is called Green AI for a New World, where we try to tackle different green AI techniques inside of sensors to try to fix those distortions in real time. And now we are using WNNs as embedded software techniques to try to correct the distortions on cameras. If we could use this as a filter, real-time filter, to very traditional techniques like common filter, this is a very powerful approach. Not done yet, we're still working on this. And we've been using this on the Lua robot. Lua is a robot from the Nautilus competition team. We've been working on this. We use tiny machine learning approaches to combine algorithms to do beamforming. And the result with beamforming usually goes from use time and frequency to map the beamforming sequences. Time is has a lot of resource consumption. Frequency, there's a lot of mistakes instead. So we can use machine learning to map the best frequency to use inside the time approaches, reducing resource consumption. The result is pretty awesome. And again, the best result was not neural networks, about using clustering. And we use Python, use ROS, Robot Operating System, using a Jetson Nano to do this. And the result is awesome. This is a SLAM using our beamforming approach. The ground truth is this one. And the common filter using our beamforming algorithm is this one, pretty close. The path planning, was amazing. And we now have a student doing undergrad final project on this, and a pretty good result too. So another thing that we are working on, but this is a cooperation with the University of Cork. It's about Internet of Bio-Nano things. So we have bio-nano machines that are like cell organisms created only to represent sensors inside in places that sensors or machines are not good enough, think like your body. So instead of placing machines or nano machines inside of your body, I'm placing well-engineered cells inside of your body to try to map stuff. And for actually not only your body, but in some place like places where you have like chemical weapons, this is especially good enough. So the idea that I have, instead of have traditional wavelet communication, radio sequence frequency waves, I use molecules as a method called a molecular bit. And we work on pheromones in the last work, also from 2023. And we built a system using Bayesian networks to map those things. So we are trying to propose a low-cost interface for long-range Internet of Bio-Nano Things communication through indirect sensing. So the idea is that I have a biochemical signal, and I will have a conversion unit, and this conversion unit will apply a filter, and this filter will be a Bayesian network about my elements. So I know if there are some types of elements, such as some pheromones in the air, the temperature and humidity, and if it's raining, I want to detect if it's raining, if there will be a high precipitation range. I know that given a pheromone in the presence of water, increase the alcohol level in the air. So this is an indirect way of trying to map those things. And this is very powerful, because now I can use a very cheap, a very trustworthy and very reliable and self-replicant organism inside of my environment to understand if there is a chemical attack. I can use organisms inside of your body to know if you have a high sugar level on your blood. And this does not create environmental problem, because it also dissolves in the air. So this is a very powerful way. And instead of trying to map and to understand the molecules, each molecule like it was a bit, I'm trying to do, say, like, if this level of organisms are in the environment, how it changes the environment, and I'm measuring this. And this is pretty inexpensive. I use a Raspberry Pi to do this too. And the last work that we are working on, it's about detection of the large precipitation. So to detect if it's extreme rainfall, nowadays you use what called numerical weather prediction algorithms. They are pretty expensive, even in face of machine learning. What we're trying to do is to use data fusion techniques to compress the data and try to extract features from this data to try to build extremely cheap and low-end devices to predict extreme rainfall in cities that are very poor, especially in Brazil. So instead of trusting a big center that will produce computation and send message, I can use like Raspberry Pi to try to detect extreme rainfall. And we use a DNN approach called SmartUNet, UNet a transformer approach. And this SmartUNet, we use data fusion algorithms inside of the data of the satellite data to compress this data. And it was very, very powerful approach. And we published this on the MFI conference, that I can say that MFI is like a sister conference to Fusion. Yeah, a system, because most of people that is in Fusion also using MFI. So it's a pretty interesting result. And we used working on do a federated learning approach in this type of algorithm to reach. Imagine that you have like sisters close to each other, like in Rio, you have Petrópolis, you have Teresópolis, cities on the mountains that can exchange data between themselves to say, okay, guys, you need to take care of, call the firemen, call the authorities, prepare for, because big rain is coming. So, and what we are doing this year, we are working on what we call small generative models. Instead of using ChatGPT for everything, imagine that now I can place a generative model inside of a sensor. And the sensor can now produce data and try to predict their own data based on a time series analysis. And this is a work that we will publish in the next few weeks, that we'll be submitting to in the next few weeks. And this is a paper from last year, the era of 1-bit LLMs. And we are using small generative models inside of IoT sensors using federated learning to give those approaches. And the results are awesome. The results are pretty good. And not only I'm worried about this, but also Meta is working with this. This came from Yandy Kuhn, no? And this is a LinkedIn post from him, I guess, from 6 months ago. And the results are coming. This is a robotical farm that we built with FUNAB, Universidade Autônoma de Bucaramanga, in 2017, when I was a visiting professor, an online visiting professor, what is a very interesting and cool stuff. This is an Nautilus robot now, as it is nowadays, in the white cup. That's a IoT cup that analyzes milk quality in real time using data fusion and tied machine learning. And we won in Vacathon. That's the best name. Vaca in Portuguese means cow, and Vacathon is the best name of hackathon ever. So it's we won in 2020. We're using with UFRJ students, and this is pretty important and good result. And we are using these techniques nowadays in farms in the northeast of Brazil too. So just to end this up, because I think I'm a little past the time, things have their place on the internet. Better monitoring means better data means better decisions, and better decisions means better policies. So if you can enhance the data from the sensors, imagine that this will be 1.5 trillion devices, and this will be most of the internet. We can have better data. And I would like also thank my students, my team. No one works alone. So a lot of people, CJ is a little bit fatter with more hair. So time passes, but my beard is also whiter than it was. and a lot of people passed through the lab throughout the years. So thanks for all these people. We are here in the second LaFusion, and next year is Fusion. So don't forget about it. We'll keep discussing those things on Fusion 2025. Next year on July, and this is one of the main targets of LaFusion, is to foster the interest in data fusion in Latin America and bring people to this conference. And we believe that LaFusion is a free conference because we want to share this knowledge in Latin America. It's pretty important, and to bring people. So try to come, try to enhance your work. If you didn't submit to LaFusion this year, think about submit to Fusion next year and to LaFusion 2025 too. Thank you very much.
We have time for a few questions. Please.
From YouTube. It's from YouTube?
No, from YouTube,
Okay,
we don't have any questions. My question will be, would you say that time machine learning is already popular in the main companies, or is something that it's being built in time?
I think the time machine learning as it is nowadays is popular from the companies that are already working on IoT. They see this as the next trend. So if you go to like Google, if you go to STM, if you go to Microtensor, those guys are working on time machine learning. But even the time machine learning foundation now changed its name to Edge AI Foundation to get a bigger and broader perspective on what it is. So at the same way that IoT began as wireless sensor network for most of people and evolved to IoT, time machine learning began as a topic because it was artificial intelligence IoT, it was embedded machine learning, time machine learning. Now we are placing everything on Edge AI. So we are going to this direction, this research direction. That I think it's fair enough, and we see a lot of Edge AI conference coming around, working on federated learning and those things. So that's the place we are going to right now. So it's already on. A lot of products going on this, but it's still a lot of work going on because most of people just place things on a power plug and use neural network, and this is Edge AI. No, this is just bad at Edge AI. So we have to work on good stuff to be like an area that will be still going on throughout the years. So of course, each time that passes, we have more resources on end devices, cheaper. But just because something is cheaper doesn't mean that you can't optimize and can't have better results with less resources. And that's something that I actually believe that is a problem, because in some point in the last 15 years, we decided that since computational resources were available and cheap, we could just do bad software. So we have to rethink this, to try to go back to do lean software, optimized, well done, instead of just doing lots of code and hope for the best.
Hello. Tuesday, we have a lecture from Professor Santiago about green AI.
Yeah.
How you see the connection between TinyML and green AI?
Yeah. Actually, me and Santiago, we founded a group, interinstitutional group called GRAIN. Me, Santiago, and Professor Leopoldo Luschino, that will be on the panel tomorrow. We are discussing the environmental impacts of AI. So time machine learning is one way of thinking green AI, like the optimization of resources, and the more resources in machine learning does not directly goes to better precision. And that's one of the main inequalities of machine learning. Most of the time, data cleaning, better architectural thoughts, or architectural modeling about the machine learning results in better results than more data. So this is one of the incoherence of the machine learning behind that we are going right now. And machine learning is important, AI is superb, but we still have to think about the architectures of optimization. This will lead us to better results with less resources, not otherwise. And that's what GRAIN is all about. And GRAIN is one of the supporters of LaFusion since the first edition. We are group, we are trying to achieve this in together and foster people to discuss not only the software about it, but the philosophical aspects about machine learning and how those things go. So green AI is a big aspect of time machine learning. Is what we're trying to do right now. So the hyperdimensional computing, the specialization of Professor Santiago, is also one of the techniques that we're trying right now. So we are trying to find ways to share a student, me and Santiago, and Leopoldo also, we already share a student. So we are trying to foster this type of collaboration to the next 15, 20 years, although Leopoldo will say that he doesn't want to work for more 20 years. But, well, that's it.
Thanks, Claudio, for the very nice and rich presentation today. I have a question regarding the radar-like application with the Jetson. Are you feeding the network with a camera image and recreating the depth map, or are you simulating the radar? It's not clear.
I'm feeding with camera data.
Camera.
Yes, we get camera data, and now I'm trying to reproduce this data in real time and to correct this data. Imagine that you have like a drone, because we have this project in LaFusion called Arpia, or Harpy for you on YouTube. The Harpy project is a drone project. So my drone project has to be really reliable in terms of energy consumption. So one of the ways to do this is to use those weightless neural network as a filter for the data that I'm collecting. And one of my first experience of autonomous vehicles is that I had a UAV that had just a webcam as camera underwater. For those who has worked underwater, to have just a camera underwater is almost the same thing of being blind. So it's like you have like just one eye, and this eye is a very bad one. So what we're trying to do is, okay, in the air is better, but you're moving faster. So how can I try to adjust these images, given that I'm moving through faster? So I'm using this active recognition, using the weightless neural network to try to stabilize the images and do the recognition of activities. So this is what we're trying to do. And then to reconstruct using the WNN that gives my radar. So the radar approach is in the IMU of my drone to try to enhance those. Since I don't have the best hardware, can I emulate this behavior through software? And the answer is yes, kind of. Because I think there's some things that better sensors cannot be replaced, period. That's but a lot of the okay sensors can go to a very high regard of accuracy, recall, precision, by applying the right filters. That's what we are going to.
And a bit more technical question regarding how do we encode the data from the image to feed the weightless neural network? I suppose you're restoring their binary sequence.
Yes.
A sort of.
This is an excellent question, because we have to not only store the RAMs. The RAMs are the units that will work as the weights, let's put like this. It's not a real weight, but we have to compress those run images. So we have like a compress, decompression. So I do 2 transitions of processing to use the RAM. So I took one of the RAMs, I compressed, decompressed. There is loss of data in this, but it's okay. And then I can use this process, compress again, and like storing, I'm working off the memory all the time. Nice. But it's still cheaper than transmit.
Yeah. I'll be very glad to see the paper.
Perfect. I can share with you. It's a pleasure.
Thank you very much.
I'm still working on a new step. I have a student that should defend until December, hopefully. That will work on this too.
Okay, I have a question about the LLMs in the small sensors. In a network of sensors, how is the problem of bandwidth between them? Do you have to have increased bandwidth to enable the federated learning, or no?
No, we don't. I use ZigBee protocols. actually like to. One of the things about Zigbee 802.15.4 protocol, it's the lack of availability. Most of the products don't have them, Zigbee protocols, but I like to test things on Zigbee because it makes me very conservative in the ways of exchanging data because of the low data rates. So the idea is instead of transmitting data, try to transmit symbols. It's much cheaper instead of transmission. I'm not interested in transmit data anymore. I'm instead of interested in transmitting perceptions. I use the generative model to see if the data that I'm collecting, it's what it's supposed to be, or if it makes sense. So I use the generative model as an anomaly detection real time. So my data, my transmission is not about the data anymore. My transmission is about I'm in the right way. I'm going where I'm supposed to go. I'm trained. The problem is I still need to be pre-trained networks. So it's not something that I was able to fix up to now. This is a very personal work. It's not something that I've shared with my students yet, but I was not able to fix this pre-trained approach. I've tried to do, but as I try to do online training inside of the sensor, the energy consumption is high, and it deteriorates very fast. So I still don't fully understand why. I have some guesses, but I think it's because the nature of the data you collect. But since I use this small model, now I can try to see this data makes no sense. So maybe the sensor is defective, maybe the sensor has a problem, and this led us to explain the situation of the sensor in real time.
Perfect. Let's thank our speaker for a nice talk and tutorial. So we will have a break now and reconvene at 10 for the next tutorial. Thank you.
Thank you very much.
falar assim, aqui, aqui, aqui. Sempre assim. Nessa distância fica excelente.
instantinho. O outro daqui para vocês. Hey guys, thanks. For the second tutorial of the day, we will have the introduction to data information fusion, concepts, challenges, and techniques, an overview focus on the maritime surveillance domain. The instructors of this tutorial will be Pablo Rangel, that holds a PhD and a master's degree in engineering from the Federal University of Rio de Janeiro, as well as a bachelor's degree in computer science. Dr. Rangel is a researcher at the Brazilian Naval Research Institute, IPQM, where he works on several projects in the area of command and control, tactical systems, navigation systems, combat systems, and simulator. As a researcher, he has published scientific articles on software engineering, artificial intelligence, and data fusion, both in Brazil and internationally, in addition to articles for scientific dissemination. As a software engineer, he has led the development of complex systems for various sectors of the Brazilian Navy. Dr. Rangel also serves as a professor at Estácio de Sá University and Infinite Institute in Brazil, teaching courses in both undergraduate and postgraduate programs with extensive experience at Estácio de Sá University. Dr. Rangel served as the head of information systems program and designed the software engineering bachelor's course. He also creates IT training, content consulting technology, and review textbooks. Dr. Rangel is the author of Object-Oriented Systems, Theory and Practice with UML and Java, published by Brassport Brasil. José Gomes de Carvalho Jr. holds a PhD in engineering from the Federal University of Rio de Janeiro and a master's degree in engineering from Fluminense Federal University and a bachelor's degree in electronic engineering from the Federal University of Rio de Janeiro. Dr. Gomes is well known for his contributions for the Brazilian Navy across various areas, including command and control, tactical systems, navigation systems, combat systems, and simulators. With over 40 years as a senior researcher at the Brazilian Naval Research Institute, he has contributed extensively in fields such as artificial intelligence, data and information fusion, and other subjects related to military application. Dr. Gomes also served as a field professor at Estácio University and several other institutions for over 25 years, teaching courses at both undergraduate and postgraduate levels. He's the co-author of the book Object-Oriented Systems, Theory and Practice with UML and Java, published by Brassport. So thank you both Dr. Gomes and Dr. Rangel for your tutorial. Welcome and feel free to start.
Hello, good morning. Is everyone okay? First, my apologies. I'm supposed to be the first tutorial, and I faced a huge traffic in the morning, Rio de Janeiro, right? And it's really hard to. I'm supposed to be the first because it's hard to talk with the audience after Claudio. It's always hard, right? Because you know them. And we have today such good tutorials with a depth of knowledge. However, we thought about a tutorial with just the introduction for beginners, for students, talk about the concepts, challenge, and we work in Brazilian Navy, so we thought that maritime domain will be used as the study case of the concept that we're talking about. So what, why, and where data fusion uses is basically the agenda we'll follow. DDL meta model, it's the basic framework that we use in data fusion field. Data fusion maritime domain, goals, sensors, and architectures. Data fusion is level 0 and 1, and we have demonstration, videos, and a simulator to show. Data fusion is level 2 and 3, and our conclusion. So I start with something like silly, right? What is data fusion? Well, combining data from different sources. However, to start about this subject, I need to present an example. So, Professor Claudio has many students, right? And he's well known by his texts, his exams. It's really tough, I think, right? And think about a not well-prepared student. Let's say something like that, not well-prepared student. Well, this student chose a better place, let's say something like that, in the classroom, where he can see the answers from different other free students, right? He can see the answer of free students, different free students. And the first student for the question 1, he answered letter A. And the second student answered letter B. And the third student answered letter A. So we have 2 students with letter A as answer and 1 student as letter B, right? So what's your choice? A. It's the intuitive, right, choice. Because you say, well, I have 2 letters A, maybe they're right. So you're creating intuitive, a voting system in your mind to choose letter A. However, if I say to you that the second student that chose letter B is the best student in the university, and he has the highest score in the universe, do you keep your choice? No? Why? Yeah. So that, yeah, you can trust more. Yeah, that's about data fusion. You have different sources, you have different students. I don't know if it's a good example because I'm in the university, so maybe you are wondering why Claudio is okay with that, right? Maybe because he's happy because we are Botafogo supporters, we are Botafogo fans, right? So we are happy, so whatever, right? So that's not the time. So that's about what is data fusion. It's about to know what the sources you have, what the kind of noise, error, reliability, how can you trust these sources, combine these answers, right? And you can have some kind of unprecision because maybe you are not seeing very well and it's letter B or letter D. I can see correctly. So that's about data fusion. And make choice properly according to the sources is a challenge when you are dealing with hard problems. So why do you need it? Right. Well, of course, it's because I need to improve my accuracy. I want a better score than as possible, right? Increase efficiency. I can have a new insights because when I see the text of the Claudio, the exam, I can see that he chose 3 questions from other past texts, right? From 3 years ago. So the students are keeping the past exams and see a pattern of using this text, right? We are professors, we know that sometimes we reuse those questions, right? And it's a common thing. And of course, it helps with decision making. So there are a bunch of domains that we can apply data fusion. We're talking about military defense because that's a thing we are used to develop. We're used to develop military systems, especially naval warfare. Autonomous vehicles, so we need to combine sometimes a LiDAR sensor, GPS data, odometer. We can create a route, a safe route, combining data from different sensors to autonomous vehicles, a healthcare. We can see blood tests. We can see your actual symptoms, combine them with your historical of patients, and know with his health issues, climate weather, predictions, rainfall, financial service, right? Because we work with data fusion, so people that works with data fusions are rich, right? Because we're working, right, Professor? So, and industrial automation. And there are many tasks in data fusion. The first one is data integration, combining data from different sources, right? And different representations into a unified representation. So sometimes we are getting information from text, from numbers. We have different formats. We need to unify now one representation with different ranges, right? We need to perform a normalization. Association, we need to know the errors, precision, accuracy from different sensors, labeling according. Correlation, we need to know the relationship between those data. Reconciliation, we need to see conflicts. For instance, we can have data from different GPS. We need to know how can I trust different information from conflict information from different sensors. And interpretation. I mean, that's the reason we need to know the meaning of the information that we are gonna have combine those data. And there are many challenges in data fusion: imprecision, vagueness. So the temperature is high. What do you mean with high, right? Or low, or fast, or, I mean, there is a, sometimes you need to work with techniques dealing with unprecision words. You need to know how to create and create a numeric value to represent this information: ambiguity, conflict, granularity, accuracy, and of course, intense computational process. So the reliability is the main problem when we are dealing with data fusion. So when we look at the JDL model, this is a standard model. There are other ones, but this is the standard, and there are revisions about this framework. But considering the standard, we have 5 levels, right? And in this tutorial, we are going to show examples in level 0, 1, 2, and 3, right? And it's basically an incremental process, right? Since you have the data from the sensor and process over the layers. And the level 0 is about to interface with sensors, getting the data, avoiding the noise, dealing with the errors, right? We have the level 1. And if we look at the maritime domain, we are able to estimate the state of the objects. For instance, we have a ship detected, a target. We can, in this level, know about its kinematics, such as position, velocity, and stuff like that. Situation refinement in level 2, that's related to know what's the meaning of that object. It's a cargo ship, it's a fishing vessel, or it's a military, it's an enemy, it's not an enemy. And in level 3, we are able to see if it represents a threat, right? What's the intention? It's it's going to engage against us. So this is about the level 3. And the level 4, it's related to have the feedback of the results and put the results in the previous layers to increase the performance of our models. Sometimes you don't have in your system all layers. Sometimes you have just level 2 and 3 because you have the information from other system or other device. It's not basically an obligation, but you can have all these levels. And level 5, you have a feedback from the user, and you can improve the results considering the user's interaction and the system.
Okay, now I'm going to talk about the level 0 and level 1 in the maritime surveillance systems and naval systems as a rule. Oh, sorry. Oh, that's difficult. Here it is. What kind of entities we have in a naval system? You have ships, vessels that may be military or civilian vessels. We have airplanes. We have oil platforms, and all these elements that compose the environment are monitored by sensors like radars. There are different types of radars, like cameras, like equipment that detect electronic emissions. And all this stuff is used to, firstly, to answer these questions. Are there someone of interest in the environment? And how many of these interest objects are in the environment? So it's a detection task that involves some filtering, since this information can be noisy. After that, we are going to we need to produce some information that is not provided by sensors. For instance, radars just provide position, but you would like to estimate the speed. You would like to estimate the heading, the course of the ships, of the objects, and you also would like to classify them. So you are trying to answer these questions. Then where are they and how do they move? And after that, when you already know the entities that are in the environment, you will probably it's useful to discover some other relationships between them. So it's useful to answer these questions. Who are they and how do they group? What are they doing? Are there any work in progress, like a fishing activity or military ships that belongs to a form that has an specific intention? So clustering tasks that bring relationships between these elements provide a better situation awareness. And this situation awareness keeps up to the next level. That is the evolution, the forecast, the provision. Where are they going? So we are trying to answer these questions. Where are they going? What do they intend? What can we do about that? So that's the main functions of command and control systems: to monitor the environment, to understand what's going on, the situation awareness, and to plan what we can do about that in the future. So for this, we are going to use some specific some sensors that are very common in this environment, that are radars. There are many types of radars: navigation radars, search radars, surveillance coastal radars, and all of them provide position about the objects in the scenario. Sonars and EMS equipment detect only the bearing of the direction of the target. The AMS and AAS and ADSB provide what we kind of voluntary information that may be not reliable. Tactical data link provided reliable information, since they are provided from our friends. Cameras and satellite image can provide information about positions and classification of the targets. And external systems can add a higher level information from these countries, from these objects of the environment, like informations provided from other countries or from intelligence agencies and things like that. So all these sensors, all this information provided by the sensors may be fused, and we need an architecture to do that. the most simple architecture is a central data processing, a central data fusing that deals with raw data provided from several sensors. But this may be costly, since raw data are voluminous, are huge information, a huge amount of information. So we have transmitted this to a central data process, and you have to process this, and this may be a bottleneck, a processing bottleneck to the architecture. On the other side, you can decentralize all the processing. So you have local data processing that deals with the local sensors. What makes sense, since the local sensors probably have the most part of fusion task. And then all these nodes talk with each other, and that may be a problem, because you have to control all this communication. But it also may be a problem if you have not connection between them, and that's why there are a third option that we prefer use in our applications. That's a hybrid or hierarchical architecture, where each node that has a local data processing deals with the same local sensors as in this architecture, and provides to a higher level the fused information. But the situation awareness is a global situation awareness, since we have these connections. But in some cases, we don't have these connections, then we can provide for this node here local situation awareness that's good enough, or that's what's possible without connections. And in this architecture, if you have all the connections, so the global situation awareness can be spread down to the nodes. So everybody has in a better situation, everybody has a global situation awareness. The global situation awareness is spread among these nodes if you have the connections. And to understand how this is important, you need to understand how does it works how does the functions are spread in a real situation. We have a strategic level. There are three levels of operation. There is a strategic level, an operational level, and a tactical level. The tactical level is where is done by the ships, the ships or the troops or the airplanes in the sea. Of course, sometimes they are doing collaborative operations, and this collaboration is provided by a tactical data link that enable them to exchange data. Sometimes they operate on a solo operation, and all these operations are controlled and are planned and controlled by the operational level that it's on land. There are several units across the coast that can capture from this ground surveillance stations data and provide all this data to a regional center that fuses these informations, not only those provided by the ground surveillance stations, but also those provided by the tactical operators that provide this by connection, a satellite connection, or even by radio here on the ground. So all these two levels here, the operational and the tactical level, is the main level. There are fusion in both of these levels, and this is the main job of the Navy. Here, the strategic level is in the domain of Ministry of Defense, that join this information from Navy with information from the other Army, from the Army, from the Air Force, and other informations, and make strategies to the road process. So our main problem is to integrate the operational and the tactical level to in an approach that can combine the advantage and the disadvantages, the advantage and disadvantage of this operational environment when we have or not have connections. So That's why that previous architecture that I've mentioned 2 slides ago is a better one. Since we can have a local processing in a regional center on land, provided by sensors from the ground surveillance stations. From these ground surveillance stations, we have a core that's based on a tactical, on the tactical level, with some ships that are integrated by a tactical data link, or even from a vessel that's operating in a solo operation, but that has too many sensors that must be fused to send it to the high level. And the problem of being a bottleneck, it's decreased since we have a low amount of fusion here, and even the availability of the node can be done with software engineering resources, tools that provide redundancy and online changeover from one node to another. So in these situations, in the tactical level, perhaps you have operations when the 2 or 3 or 4 vessels are operating connected with each other by the tactical data link, but one of them has not a radar, or has a radar, but it's not his interest to turn it on for security reasons, for instance. So everybody here, every ship here can construct his own local situation awareness based on his own radars, his own sensors, or the sensors from one other ship, or even only for the sensors from the other ships with sensors from its own ship. So this tactical operation can be connected with the operational level, or can be not connected to the operational level. So that's important to understand that local situation awareness may be the best you can obtain in certain situations. Of course, the barrier is a global situation awareness, and it will be possible by this architecture if you have a satellite connection. And the same will occur with a single ship that usually has three or more radars or in other sensors. So you must fuse information, and this information that is fused from the radar interception coverture is called the plot fusion. So you have plot fusion areas here, you have plot fusion areas in a single ship, you have plot fusion area from the ground surveillance stations. So the plot fusion is the first task that we do in this fusion process. Well, the role process includes monitoring, understanding, and planning our actions. And then you have the entities of the real world, the sensors reads these informations, and you produce a detection. You prune the clutter and produce a detection and estimate some things that the sensors doesn't supply. For instance, radar only supply position. You can estimation. You would like to estimate velocity and velocity and course. And after that, to a better understanding, you have to classify or to clusterize the objects in the scenario, and in the next level to make decisions to predict reactions of this situation awareness. Well, so in each of that nodes, we have fusion in 2 levels. Now we done it in 2 levels. First of all, the main sensor is always the radar. So we have different radars that all them produce plots. There are position information about the objects in the environment. Then you fuse only information from radars, and we produce estimations of speed and course of these targets from the real world. And this is what we call radar tracks. But this same object of the real world may be transmitting by the AAS equipment information that, as I said, are not reliable. You can, it may be true or not. But these AAS tracks have information. And also we can have sonar tracks provided by a sonar equipment. And also we can have this same vessel can maybe captured by another ships and transmitted by a tactical data links for your ship. So you have TDL tracks, sonar tracks, AAS tracks, and radar tracks, and you have a second level of fusion here that we call track fusion. Then, besides providing a solo vision, a solo information about this object of the real world, we also add information provided by different sensors. So we have a position, a course, and a speed that is estimated by radar tracks. We have general information from AAS, origin, destination, for instance. Information provided by TDL that may be a hostility information, a classification information, a classified information, so a security information. So all this is added to the tracks to provide a better situation awareness. So it's important to understand that these two levels of fusion, the plat fusion and the track fusion, is provided in each regional center. A regional center may be a regional center on ground, maybe a group of vessels on the sea. We have already seen that. So the plat fusion is done. After that, the track fusion is done with other sensors like AAS or other sensors in this locality. And all this stuff from all the regional centers is provided to a main center that has the task of fuse this information with external systems and provide back to the regional centers the global situation awareness. To understand, to better comprehension of what are the plots and how do they look, I'm going to show you an actual surveillance, coastal surveillance radar that's here in Guanabara Bay, exactly here in the IPQM site, and this is bota aqui para tocar direto. Here. Okay, so it's providing information about the environment, and you can see that there are many clutter here provided by buildings and from geography on land, and a coastal detection. There's a detection of the bridge from Rio de Janeiro to Niterói here. There are many other detections here on the sea that are provided probably by vessels, but also may be clutter. Here in Guanabara Bay, there are lots of clutter, but on the sea, on the Rio, there are many clutter. So, tá bom. Next. So the raw video need to pass to a card. That's a COTS equipment that makes the conversion from analog to digital and applies some initial filters to filter the rain and the wave plots and produce plots, but still with some clutter. And these plots from different radars are then fused in this firstly plot fusion. And this produce plots fused from both the radars and goes to a tracking estimation. That's an iterative process, since you have to observe the plots for a period of time to be sure that they belongs to a real object of the from an object of the real world. So after that interaction process, you estimate radar tracks that are also then will to the next level. That is the track fusion. But after that, how does it work? The tracking estimation model is a mixture. It's called the interactive multiple model. Of course, there are other techniques, but we use this iterative multiple model. That's a mixture of common filters. Each of them prepared to a kind of motion, a rectilinear motion, accelerated rectilinear motion, or a circular motion. You can construct other ones, and then you make a weighted average of this of the outputs of these filters to produce the predicted state, the final predicted state. You can see this here in this graph on the right. The blue trajectory is the trajectory of the real target. It's not a straight line, since there are a process line included in it. It's a simulated signal. So you have a process error that is included in this trajectory. And the red crosses here are the measurements done by the radar. So there is a single target and a single radar here, and they are the radar is producing measurements about the position of the with an included measurement error for this radar. And what the mixture of common filters does is produce this black estimation that's closer to the position of the target. So it mixes the actual measurements with the previous estimation to produce a new estimations, and with a longer run here you can see the trajectory in green for the target. The measurements from radar are the blue points, and the estimation produced by IMM model is the red trajectory. Okay, but how does it works if we have? How does it works if we have more than one radar? How does we fuse the plot? What's really the plot fusion? Here we are going to play a video now, but here we can see the measurements of this is the real target. And this is measurements from two different radars, a red radar and a blue radar. And they are producing targets, and we are not having a track estimation. Now it ensures that these measurements belongs to a real target. And he starts a track here. And he updates this estimation from each measurement of radars that it receives. So the plot fusion, it's exactly the same that estimation with a single radar. You only makes a new estimation for each measurement that you receive. It doesn't mind if you receive it from radar blue or from radar red. You just update your estimation for each measurement. So that's the plot fusion. The plots are fused from 2 or 3 or 4 radars, since they will be considered being from the same target. So after plot fusion, we produce the radar tracks. So we go to the next step. That is the next step. That is the radar track. Well, but before showing you the track fusion, I will present here some the role process going on with more than one radar and more than one target to a better understanding, so a better comprehension. So here we have. In this environment, in this framework, we have a target simulator. So we create a target, we will define a type of movement to this target, and we define some process error to this trajectory. And then it will produce targets that will be passed to a radar simulator. And the radar simulator, you can create the radar, define the parameters of the radar, and define a measure error to these radars. And they will produce plots plus some clutter. You can define also the density of the clutter of these clusters, different densities for different radars. And all this information is passed to the plot extractor that works together with a track estimation in an interactive process, and will produce the tracks in the final as the output of the process. And all this stuff, the plots plus cluster from each radar, the tracks provided from the track extractor, and the targets will show will be shown in the visualizer viewer here that present all the scenario. So let's practice using our simulator. I have to change to. Let me run this tractor and the visualizer. So here we have. So here we have the scenario is the Guanabara Bay. I will firstly create a target here. No, sorry. I will create a target. I will create a target. I will give it a direction. For instance, 090. I will give him a velocity, 8 knots, and that is. Now I'm going to create another target here. It's a different direction. It's a different velocity. Knots. Okay, that's it. Now I'm going to hide this information, the information about the real targets. I'm going to hide it. And now doing a zoom out to in the environment, I will create a radar exactly here where you have seen in the previous slide. That's the located where is located the radar of high PQM. I will insert the radar here, okay, with that's an RPM of 30 revolutions per minute. Okay, we can change the we can change the error here or the probability of detection, but let's do something simple at first. So for this radar, I'll give some I will put some density clutter, a medium amount of clutter, and I will turn it on. Okay, now when I turn it on, he is detecting the coastal, and he is generating some clutter, detecting some clutter provided in a medium density, and also detecting the targets. But where are the targets? Where are exactly the targets? It's difficult for us to understand, and the model is trying to understand also where are the real targets. So it associates these measurements for a while, and sometimes it's going to be detected. They are going to be detected. Here it is. They were detected. So now let's introduce another radar here in Niterói. And this radar with a different rotation per minute, and I will give this radar a different amount of clutter, a low level of clutter, and I will turn it on. So now we have two radars detecting the coastals. The coastal. We are two radars generating plots, and all this stuff is fused by the estimator. Is being considered by the estimation. So if you come and zoom in here, and we put the target again, you can see here the measurements provided by the blue and the red radars, and the estimated track, and the position of the real target. That is this point here. Okay, it's quite accurate, the estimation, but now the target's going on a straight line, and I will maneuver this target to a circular maneuver. He will start maneuvering around this point here, and now suddenly change the movement, making maneuvering, and the measurements from the radar are still arriving, and are still being considered in the estimation. And the new course of the vessel was discovered by extractor, and now he's turning around this point. Now I will complicate it a little more. Here is the region of port of Rio de Janeiro port, and I will create a radar here, but now a radar with a movement. That's not a land-based radar. It's a ship-based radar. So I will create this with also 2 seconds information, 30 revolution per minute, and I will give him a direction, and I will give him a velocity, 12 knots, and I will turn it on. And now he's generating his own plots, and all these plots, the yellow plots now, are also being considered in the fusion of the track. So here we have, if you make a zoom in here, you can see yellow plots now being produced by yellow radar, and the radar is on movement. He is going on with a ship. So the process works for radars that are based on land, and the process works for to mix information from radars on the sea from different ships also. Okay, I think it's enough. Now the next step is this was the plot fusion and the track estimation, and now we have plots from track, and you have to fuse them with plots from other sensors. So we have the step of track fusion. The track fusion is done considering that all the estimations are good estimations, but we don't know the covariance metrics of those estimations. We don't know how the AAS does his estimations. We don't know how external systems does their estimations. So we have to create a hypothesis test to test if these different the measurements from different origins belongs to the same object in the real world. So we create a variable that's the difference between these estimations, and this difference has a Gaussian distribution, you know. And then we create an auxiliary variable that is a sum square of these Gaussian variables. The math involved in this conclusion can be found here in this reference. But this is a variable that has a different distribution, a chi-square distribution. That is a tablet distribution from where you can pick up with a certain grade of confidence. We use 99.5% of confidence. The value that X must have to deny or confirm our hypothesis. The hypothesis, the measurements belong to the same object in the real world. So we just calculate this difference for some time, calculate this variable for the same time, compare this variable with the chi-square table, and decide if we deny or confirm the hypothesis. So this is done with sensors that provide the same information. Radars and AES provide position and speed and course of the targets. But what happens if you have sensors like sonar or EMS that only provide bearing? Then you have to use a different vector state. You have to use the bearing and the variation of the bearing that's angular velocity. You mount a different state vector for the sonar and for the radar, and then you make the difference, and the roll. It's the same process that the previous slide. You calculate this variable, this scalar variable here, compare with the table of the chi-square distribution, and decide if you confirm or not the hypothesis. Which is the problem with this technique? The problem is that you are comparing, you are testing the hypothesis of two measurements belongs to the same object in the real world. But how many of these data are in a real situation? We can have dozens of origins, different origins, and thousands, hundreds of thousands of different objects. So it may be costly, computationally costly process. So in a real situation, we can have 400,000 vessels in the real world. We are monitoring this amount of vessels in the real world, and each, if you have 10 origins, that it's not enough. It's a conservative estimation. If you have 10 origins, so you have to do this, or this for all these vessels. So we divide the problem, making firstly a cluster process that it doesn't make sense to compare a target, a measurement from a target here in Guanabara Bay with an information from a target in China. They are not the same vessel. So we group them in certain regions with a cluster algorithm. We use K-means, it's a simple algorithm, and then we apply the hypothesis test, only the track fusion process, only between these grouped vessels here. So does it work? Yeah. This is a pre-script from a real system that controls that is used in our Navy. And here we are showing just the fused tracks. And even here, only in the Guanabara Bay, you have all these fused tracks. We are showing here only the fused tracks. And I have this amount of tracks fused here in Guanabara Bay. And we are monitoring, in fact, 320,000 of vessels in the real world. And from these thousands of vessels, 22,000 are being fused with this process. And one of them, for instance, this one here, is fused from 7 different sources, including radar. So it is passed by a plot fusion, and then generates a track fusion, and it was fused with AES tracks and with plus 7 origins tracks. So the process works, at least works for us. Okay. My colleague will now explain the other levels.
Well, I believe it works because we're still employed, right? So I believe that's so. Let's remember the concept that we have a plot. That's something detected on the environment, on sea. Can be a vessel, can be a reflection of a wave, can be sometimes a bird, right? So if it's a big bird, and in the level 0, we need to avoid these objects that's not thing that we want to detect, right? So we avoid the noise, we avoid the clutters, right? And we have the plots. The plots means that you have an interesting object. And the first step, the second step is to estimate the speed, the course, I mean, the velocity, if you want to see in a different way. And after that, we have another levels of the fusion. So we have works published in level 0 and level 1, and we have articles published in level 2 and level 3. So I'm going to show some examples about what we are doing in the level 2 and 3. Basically, we base our solutions in content information fusion, right? For the first example is about military formations. That's not a thing that civilians are used to heard about because it's a military problem. But when we are dealing with naval warfare, we are trying to understand. Let's remember the number of José Gomes said about was 400K, right? Objects around the world. So, yeah, 400,000, right? And it's hard to an operator to see that's a bunch of objects and see a pattern, right? And the pattern of the targets can indicate a military formation. What is about military formation? For example, if you have a vessel and a circle around it, can something like a cargo ship being protected to reach a destination. So this means this is important. Depend on the military formations, like a shape, a figure. If you look at these examples, means something. For example, you can have engagement situation, right? Someone's trying to defeat your fleet, right? So it's hard to someone see this quantity of targets and see the pattern. So that's the biggest challenge. And we create a model combining many solutions using a simple neural network to see these patterns. This was published in 2023. We were there, right? Remember? And that's the first time that I met Claude, I believe, United States. And the problem is quite simple to understand, because when we have a guide warship, this is basically of a military formation. One vessel, it's a guide, and the other vessels are members of a formation. So the members of a formation have a relative position and speed according to the guide warship. So we are trying to figure out how to identify this pattern, right? Looking at the speed, the course, and the position and the shape of what we are seeing in the naval environment. So the next one is about fishing activity. Usually, civilians don't know that, but Brazil, the Brazilian Navy, different from other countries, we have the mission to protect our coast, not just for defense. And inspection tasks, patrol tasks, search and rescue are tasks of Brazilian Navy. So we are interested to know if there are illegal fishing activities, such as predatory fishing, piracy, what else? Fishing by other countries, drugging, transportation of drugs, traffic, right? And many of these problems. And my students here, he proposed, implemented, and done a model that is capable to detect fishing activity. Most of these works use a collaborative information from AIS. AIS basically a transponder sending, okay, my name is blah, 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 and I'm going to Rio de Janeiro, and I'm a fishing vessel. So basically, if this vessel is sending false information, you cannot know the truth. You cannot know and no one is going to say, well, I'm going to do some illegal activities here, right? So no one's going to do that. So we base our model in a capability to understand and detect the fishing activity based only on kinematics. Because the fishing activity, each technique has its own behavior and it has own trajectory on its performing a fishing activity. For example, if you have drifting long line, right? That's the name, right? You have just a straight line for constant speed varying according to the phase of the fishing activities, if it's hauling, if it's deployment. So there is a behavior, but it's hard because a straight trajectory can be observed if you look at the Guanabara Bay right now. So that's not mean that's a fishing activity, right? Though it was a big challenge. So to solve this problem, we create a model using first position, course, and speed detected by an activity sensor, such as a radar, right? And we remember that the source must be reliable, right? I have the kinematics of the vessel being detected. I should trust in this information. And I have a trajectory classification. And how do we do that? We use convolutional neural network, right? We create this trajectory over, 4 hours, I guess, 4 or 5 hours. And the different colors mean different speeds because we want to show the different phases of the fishing. So we create this convolutional neural network, and to enhance the results that we are going to have with the model, we extract the fishing areas, looking at the past, looking at the data sets, and we compare if this trajectory is close to a typical fishing activity or fishing spot activity. So with the result, with the classes and probabilities, we have a fuse logic to combine, to fusion the both information and points out the fishing techniques, or if it's not fishing, right? So the combination of techniques and data from the past and the real past, we're talking about thousands of thousands. It's from global fishing watching. It's famous data sets about fishing activity. We are comparing with data from 4 hours ago. So when we see that, we can have fuse logic using knowledge from a specialist, and we have the fishing technique. So Another problem that we have, not just for engagement, but also for search and rescue, is target interception. So how can I have a route in the sea? Because in the sea is different from the roads, because you have streets, right, to know what the path is available or not. So I have here 2 targets. I have 1 target here, 1 target here, and this target wants to intercept this one. So how should I consider the geographic context, right? Because I have a kind of island here, right? And there is a depth, and my the ship draft, I mean, I can't pass here because it's not depth enough. So we're combining variables such as the depth of the electronic nautical chart presents and the availability of the engine of the vessel and the capability and the kinematics of this ship. So combining this data, I'm here using bathymetric data from electronic nautical chart, the draft of the vessel and the engine status, because if I need to apply a speed that I cannot do, so doesn't matter. I was not able to reach out the target. So, and I have the kinematic of the ship to be intercepted. And this is the input of a star because ant colony optimization. There are, I mean, they are famous algorithm, right? Well, about vessel detection and classification, a problem that we're dealing with, it's about dark ships. Dark ships is when our vessel just turn off the AIS equipment and you don't know the identification of the vessel, the trajectory of the vessel. And we just have the information from active sensors such as radars or cameras, right? Tomorrow, Julio Cesar will present a paper interesting about uncovering AIS spoofing and dark ships, right? Predicting trajectories. And you are prepared, right? Are you prepared, right? Huh? Okay. And here we have an image from Guanabara Bay. We have a camera in Naval School capturing this ship and giving the classification using the image of a cargo ship, right? Cargueiro in Portuguese is a cargo ship. So more than this is about the speed, the position, and the course of the ship. Here we are, this is interesting because we are not using data from radars. We are detecting the kinematic of this vessel just using the image. So this is something that we are trying to end until next fusion to publish. We have good results, and we have other works still going on with my colleagues from Embraer. I believe this is going to work. And there are main challenges such as size, occlusion, weather, image noise. My student here, Mateus, is facing huge problems with that, right? But you're a student, you need to face this problem, right? It's your turn. So the solutions basically combine convolutional neural network plus Kalman filter. And this is obviously a simplification, right? And I avoid some equations and stuff like that because I was afraid when José Gomes was, because, okay, people were being afraid of our presentation. Okay, but it ends, and I try to, this is an introduction, right? So I believe it's okay to avoid some equations right now. So I have here the convolutional neural network with data set we are building, right, with public images. And we have a common filter, and the input of this model is just the raw video. So, and we have the results combining the position, speed, and course with the classification as one result. So another work that we are dealing in Brazilian Navy Research Institute here in this neighborhood, is about to create a knowledge compilation for decision making. We are training our LLM, right, to combining data from doctrines. Doctrines are rules and military knowledge, how to conduct some operations, right? And it's not public, and it is not being published. So, but it means that we are trying to have our own engine to create a prompt for users, for military personnel, to have the answers quickly and take the fastest decision as possible. This is an example. Of course, this is all ordinary information. None of them is confidential. So this one is I like this project because involves humans. So it's like, because it's for fall detection, and Brazilian Navy has Marines, right? Marines sometimes in special operations in Rio, they are in streets, right? We have a special operation a few weeks ago, last week, right? And we have a project to monitoring position, a personal view of a camera, and the health status of the Marines. So when they are engaged in process, we believe that he's not able to communicate with someone if, for instance, got a shot. So oh, I got a shot, let me send a message. It's not possible. So we create a module to detect if he's fallen, and create an alarm to send directly to the operational center of Brazilian Navy, Command and Control Operational Center. So, however, militaries, crawls, militaries can get fall intentionally, right? So how can we distinguish that? There are some data sets, but usually to use it to elders people. So we need to create our own data set. So that is about, so we have 3 videos quickly. So can we show? Yeah. Let's coloca na página. Some people are just pretending they are carrying a gun. Okay, the sound in the background was not supposed to leak because someone is. Take out the sound, please. Can you show the next video? Okay, the best part was not that, but I don't have the video because we pushed them. It was the best part, but we are not able to show, right? And the third video. And turn off the sound because I think someone was... Okay. It's a military environment. People's yellow and stuff like that, right? So I have a military here, so okay, you can turn on. So they are wearing 2 smartwatches, here and each one fist, and a belt in the chest to monitoring. And we are fusing data from heartbeat and acceleration of the body and blood pressure and stuff like that to know if something happened to the military soldier. So, and that's it.
Okay, questions?
I have a question. Thank you very much for a nice presentation, very informative as well. I have a question for Dr. Junior Carvalho, actually, regarding your fusion architecture. As far as I understand, you're fusing the plots at the regional center. And my question is, have you ever considering doing some processing at the edge, close to the radar, before forwarding all this information, the raw data, to the regional center?
As far as I understand, you are asking if you are doing some fusion in the
Next
locality
to the radar.
next to the. Well, this can be done. This can be done in the ground. In some cases, in the ground stations and ground surveillance stations, you can fuse them. But generally, over there we have only one radar. So we have to fuse when it's necessary to fuse. So the ground surveillance stations can have, and in fact they have, interception areas, but they are located in different sites. So they are providing information to our regional centers. It makes sense to make the fusion plot in the regional center instead of inside
Sure.
the global station.
Yes.
The ground surveillance station.
I understand.
Okay.
Yes. Another question regarding the simulator. It's very nice too. Are you able to compute metrics to do some benchmarking with other trackers using that too?
Maybe done, but we haven't done it yet. A benchmark with other kind of fusion, other algorithms. We didn't done yet.
For the first question, we actually perform logo data fusion. For example, we have ships with 2 radars, right? And it can be done, right? That's something, and we perform another levels of the fusion in the regional centers because we have done raw data going directly to this regional center where we have the tracks information and the regional centers. But it's flexible to run locally or in the regional. It's something can be, I mean, yeah, it can be, there can be a adjustment, can be raised adjustment if we need. And about the benchmarks, it's a good idea. So we actually we believe that it's something that we need to provide a confusion matrix to perform a benchmark in the future, right?
That's nice. Thank you very much for the answers.
Congratulations on your presentation. I was wondering, because you've used historical data to detect phishing activities, right? I was thinking about your patterns, your patterns for vessels, and do you use historical data to detect some predictable patterns that are, I don't know, maybe each 3 months you have some kind of vessel doing some kind of pattern. Do you use this historical data also to detect this?
If I understand your question, you're saying if we use historical information for illegal activity regarding the phishing activity, or
any activity.
Any activity.
Any activity, yeah,
Yeah.
like historical data for vessel patterns.
Yes, the global fishing watching is, for instance, global fishing watch is a huge association. They have a collaborative data set, and this data set, including validated information, labeled information about fishing activity reported by authorities from many countries in the world. So we base it on our pattern recognition based on this data set. And the reliability is pretty good because was a confirmation, a voluntary confirmation by the community. So yes, we use, and for instance, the work that's going to be presented by Julio Cesar tomorrow use trajectory in past trajectory to figure out what's the final destination of a vessel, and we can expand this this idea to understand if we can see illegal activities and see illegal activities in the past to figure out if something is going to occur in the next few hours or few days, because there are hot spots of problems in the Brazilian coast.
Thank you.
Thank you very much for your presentation. I have a question at the level 1. You showed us the fusion tracks. You can have multiple sources to identify a target. And I would like to know if in this process you can estimate if there is enough source to currently map the position of the target. And I ask this with the remote radars in mind, if we can reallocate our resource to better identify a target.
No, I understand, but well, the tracks provided by several sources may be reliable or not. Okay, so if you have an AES information, it may not be reliable. Even the position, even the speed of the may not be reliable. So we have other process to prune this information. That are not directly level 1 processes, but you can prune this information. You can understand if he is doing spoofing, or that's the paper will be presented. So first of all, the level 1 information fusion is not necessarily done with all the received data. You can prune some data firstly that are not reliable, and then only consider the information that it's more reliable, of course, associated with any kind of error. There's a kind of error associated with any measure. But the process considers this error, but essentially we consider it as a confident information. Okay.
Of course, in level 1, I understand your question. Of course, in level 1, it's worse than you do in level 0, right? So level 1 is you perform level 1 when you don't have the raw data. For instance, AIS just send the track. We don't have the raw data. We don't have a detection, right? We just have the information from GPS from the vessel. So if you don't have the error measurement, the process, the error of process, so what we can bring to the table? Well, we can deal with this kind of hidden information and create model to do with this in precision, but it's not the same. But not the perfect solution. So for change the radars, that's what said, the position of the radars. That's what said.
using remote radars. In these scenarios, there's not enough data. Can reallocate a remote radar to a current position or a certain position to improve the identification, something like that?
There are different radars with different specifications and different precisions, different ranges. Sometimes you have radars that have a special mount equipment to stay inland or stay in a ship, right? So when you have a radar in a ship, you can just move in your ship, right? But surveillance station, it's a complex installation, and you are not able to move this installation.
My question is about the remote radars. They can move across the
Sometimes it can be moved. We have stations that are mobile stations, so they are mounted in a truck, and then you can move the truck to. But that's not a very common situation, a very usual situation. But yes, you can move the radar to a better situation awareness of the environment. It's possible.
But he is integrating the process.
Yes, yes. But it's hard to say that you are going to find a good spot to move a truck with a radar, right? Because, for instance, we have a radar in Naval School here in Guanabara Bay. So it's a perfect spot to see ships get into the Guanabara Bay. So there is a channel there. So maybe trucks with radars, it's something that we built together, right, in our project. The radar is not the perfect radar for surveillance, right? And you cannot move to a high spot to see the ocean, right? So sometimes this kind of solution used by Marines in their operations. So that's it.
Thank you very much.
Good morning. Congratulations on your presentation. My question is about synchronism. I don't know if it's a challenge when you are in a small environment that you have some different source of data, but when you have many ships informations and you have different data coming. You have different inputs, and so I don't know if you have some problems dealing with this situation of the synchronization, because when you are in a controlled scenario, I believe that it's different.
Yes, of course, synchronize the data, the measurements is a problem. For instance, AAS equipment doesn't provide the exact moment that they made the estimation. It's an estimator like other equipment. So we receive the information and estimates the position, but in the message there is no the time of the timestamp of the measurement. So you have to deal with this weakness of the equipment and use the timestamp that you receive the message. That's not exactly the timestamp that the measurement was produced. So we have to consider these errors in our algorithms to fuse information, because of course it's important synchronization.
Yeah. We have problems such as AIS from satellites. Maybe send you information every 7 minutes, right? That's huge. Mm-hmm. And if we have coastal AIS, we have information with 30 seconds, I believe, right? 20 seconds or less, depends on moving, right? So what we do depends on the timestamp and we extrapolate the target. So we believe that considering linear movement or something like that, we try to, but sometimes, for instance, we have sources with, 6 hours, some sources, and this information just cannot be fusioned. It's It's just we cannot use this information, right? So the uncertainty is too big to consider in your fusion process.
Okay, thank you.
All right, a big thank you for our speakers. Our next event is 1 p.m., the third tutorial. Thank you. See you then.
Pessoal, para quem não é da UFRJ, tipo assim, quem não conhece, aqui, se vocês saírem para agora, para a direita de vocês, vocês vão ter um corredor que é o corredor da COP. Vocês vão ver vários restaurantes. Aqui no F, a gente está no bloco G. No bloco F, vocês vão ter o Projects, que é um restaurante aquilo, com um preço relativamente razoável. Para o final, para o bloco H, vocês vão ter o Kilowatts, que é um restaurante um pouco mais caro, né? Mas tem churrasco para quem quiser, para quem se for importante. Se vocês forem para a esquerda, no corredor principal, vocês vão ver os traders. Os traders, em geral, trabalham com prato feito. E aí vocês vão ter salgado para quem não quiser almoçar, ou lanches de forma geral, biscoito, essas coisas, aqui no bloco da frente, tá? Esses traders são bem adequados, bem ok. Então, vocês não devem ter maiores problemas. Tem opção para quem é vegetariano, para quem é vegano, né? Vocês vão achar algumas opções. Em geral, para quem for vegetariano, tem um trailer azul no começo do bloco C, que é o anjinho, que é um pouco mais adequado, tá? Então, assim, os trailers ali na frente, prato feito, os aquilos aqui. Para quem quiser algo mais rebuscado, só que aí vocês vão ter que sair desse polo, que é o Centro de Tecnologia, e ir em direção ao Parque Tecnológico. Aí vocês vão ter que pegar um ônibus interno ou um carro, que vocês vão ter o Notório Sabor, que é no Parque Tecnológico, que é um pouquinho melhor. É um pouco distante. Para quem for andando, é uns 20 minutos andando. Eu não recomendo nesse calor. Mas para quem for de ônibus, é uns 10 minutos de ônibus para ir e para voltar. Mas eu acho tanto projetos quanto quilowatts bastante satisfatórios. E os trailers eu também como com bastante frequência, então não tem maiores problemas. Tá bom? Os trailers vão ficar alguma coisa entre 20 e 30 reais, o aquilo alguma coisa entre 30 e 40 reais para vocês, tá bom? Então, qualquer problema também eu vou ficar por aqui, vou esperar um pouquinho vocês saírem para almoçar, para caso algum de vocês tenha algum problema, tá bom? Gente, bom almoço para todos.
Hello, good afternoon. We're back. We're going to have the next tutorial. It's called Gamma, General Abstract Model for Multiset Manipulation, Perspective and Possibility for the Use of an Abstract Chemical Machine in Data Fusion Applications. The instructor is Rui Rodrigues de Melo Jr., received a bachelor's degree in computer science with an emphasis of software development from the Catholic University of Petrópolis, UCP, a master's degree and a doctorate in systems and computer engineering from the Federal University of Rio de Janeiro. His main research interests include computer architecture, parallel computing models, distributed algorithms, and high-performance computing. He's a lieutenant commander in the Brazilian Navy and has been with the Brazilian Navy Research Institute since 2006. Currently, he's the head of Digital Systems Group at the Brazilian Navy Research Institute. Please, Commander Rui Rodrigues. Thank you very much.
Hi, everyone. Pleased to meet you here today. First of all, I would like to thank Professor Miceli, Professor Pablo, Professor Santiago. We worked in my doctorate and my master degree together. And for me, is a very good opportunity to talk about Gamma, to talk about things that I did in my doctorate, in my master degree. And Pablo already present myself, but I am Lieutenant Commander from the Brazilian Navy. And this is the main subject that I worked in my doctorate, as I said, in my master degree. So first of all, just a moment. Why Gamma? The name of this tutorial today is Gamma, its perspectives and possibilities of using these in data fusion algorithms and many application domains. But first of all, why Gamma? And in that picture on the right side here, I try to demonstrate the decisions that I did in my doctorate and master degree. So when I started my master, I arrived here at this university, and I told the Professor Felipe, Professor, we need to parallelize a specific algorithm used by us in the Brazilian Navy. So my intention here is to parallelize it. And then Professor Felipe told me, Rui, okay, it's a very good work to do this, it's a very good job, but why not we solve not your unique problem, but why not to provide a platform, an environment that can be used for many kinds of application domains. So with this question, with this idea, we started studying parallel computing models to use in these applications. So why Gamma is because of this. We need to solve a unique problem, but Professor Felipe has told me, Rui, let's work together to provide a parallel model, a parallel environment. So because of this, we start working with Gamma. As contextualization, I put here some information related to data flow and Gamma. Why data flow here? Because in my doctorate, we provide some equivalence studies, some specific tools that can convert an algorithm written in Gamma into an algorithm written in data flow and vice versa. So this is the main objective of my doctorate. And as I will show you, in my doctorate, I use Gamma, but we are interested in to make some improvements in the implementations used in Gamma. So my objective here today is not to show you all of the details related to Gamma, all the main characteristics, but only an overview to introduce you Gamma and to have you the notion, why we can work with Gamma, what is the perspectives, what is the possibilities using data fusion algorithm and or other application domains. I will talk a little about the similarities between Gamma and data flow and try to show you the potential of Gamma in data fusion applications. This is the summary, but so I will start with the definition of Gamma, some little examples, and I try to run here some experiments to show you what is Gamma, what is the syntax of Gamma. So Gamma is an acronym. Gamma is an acronym of General Abstract Model for Multiset Manipulation. Many times today, I will call Gamma as a model, Gamma as an environment, Gamma as a formalism, but Gamma is a formalism. Formalism for program specification. And Gamma is based on parallel multiset rewriting. So the unique database in this formalism, we call multiset. So all of your data is into this multiset. The idea here is that element, this data of the multiset, can interact freely in a natural parallel way. So this model is a parallel model, and the programmer doesn't need to have a preoccupation of, for example, load charge between cores, to decide what part of your code will be run in another code. All of these features are transparent for the programmer. The model was proposed in 1986 by these two authors, Banatre and Lemaitre. And Gamma is a non-deterministic execution model, because the choice, when the model chose the elements that will be compute, this choice is occur in a non-deterministic way. This is the main characteristic of the formalism. In Gamma, we have the natural exclusion of undesired elements. So the computation in Gamma, we represent in reactions. I will tell you after, but the model, the formalism or the model, can work with successive refinements of the multiset. So all of your undesired elements, we can remove of the multiset. Because of this, in my doctorate, we show that Gamma is suitable to use for example, techniques for approximating computing. So that applications that you can have more precision to increase your time response, for example, you can use Gamma for this. Problems in Gamma can be expressed in a simple, in nature, parallel way. For us developers, programmers, for example, a C code, Python is something very simple to use. But for example, physicians, mathematics, Gamma can be more simpler than these kinds of programming languages. Gamma brings a metaphor for chemical reactions. In this sense, a multiset can be seen as a chemical solution. The actions can be seen as chemical reactions. And here the actions, all of your computation, all of your calculation is expressed in, or are expressed in a structure called reaction. We have two conditions. All of reactions only can execute if the conditions of these reactions are fulfilled. Only of this. Here we have transmitter, reducer, optimizer, expander, selector. This is the patterns of transforming of your Multiset elements. Now a simple example of gamma. Here we have a reaction that calculates the last element your Multiset. For example, imagine that you have a Multiset composed by these numbers: 4, 15, just a moment. Here. 4, 15, 7, 8, and 5. This is our initial Multiset, for example. So in the first step for this reaction, what this reaction means? You will choose two elements, two different elements, any elements, and if the first element was bigger or equal than the second, so your action will be remove the first one. So the first step, if the pair 15 and 7 was chosen as X and Y pair, we will have that the first element, 15, will be removed, okay? The second step is the same, but now with the different elements, 8 and 7, in this way with our X and Y pair. So in this case, again, let me see here, 8 and 7, okay. We will remove the 8th element, okay? Yeah. Now, note here, 4 and 7 with element X and Y in this way. In this moment here, we don't have the reaction condition fulfilled. So we don't have any modifications in our Multiset, as you see here, for example. And the computation is running until you have, in this case, just one element. Why just one element? Because in this moment here, at this moment here, we cannot fulfill the condition to have two different elements. So the computation stop here. This is our stop condition in this case. But you have a logical you have a logical stop condition. Gamma is a parallel computational model, but we don't have a parallel hardware to execute it. So we worked with any different implementation of gamma. The first two, sequential and MPI, was proposed by Professor Juarez Muller. And this third here, we work with this here at this university, and I will show you some details later. And what we have here is we have a code written in Gamma. So we have a Gamma compiler with lexical and syntactic analysis. And we have these three types of C code, depends of the implementation of Gamma. And at the final, we have an executable code. This is the main idea. Now I try to demonstrate some simple examples here. Just a moment, because the camera, yes, now it's okay. Let me try first show you some examples of gamma, and then we will execute them. That's it. So I will compile them here. Just a moment. Let me show you now. Here I finished to compile an example that shows the bigger element in a multiset, for example. Let me show you the code first. So this is the max is the name of my reaction. Sorry by the conditions to show you today here, but max is the name of the reaction, and this set of numbers is our multiset, for example. And max is defined as I will replace two elements by x if the first was bigger and equal or equal to the second. Just a moment. Maior. Acho que já está maior. Vai ver. Tá bom. Now it's better now. Yeah. Thank you, Juliana. Ele coloca lá. Ah, agora. Yeah. So now we need to compile again. Just a moment. Yeah. What I finished to do here was to compile and execute this code. And for result, we have this number here. That was the bigger element in our multiset. Let me show you some more detail or more examples. And then I will show you a complete example that we reproduce with a data fusion algorithm. More complicated, but just to do to you an overview of the gamma. Let me choose another, for example, a sum problem. Let me compile now. Okay, so we have 55 as the sum of these numbers here. Can you change again? Okay, I will come back with these experiments later. So before that, I will change my presentation to do to you some details of our data fusion algorithm that we produce. We using a specific algorithm that we use in a system called Cisne by the Brazilian Navy. This algorithm is called pair of plots in 2 stages. So this is the main idea. First, you have initial plots received from sensor per 2 different sensors, 1 and 2. The first sensor is the black elements, and the red ones is related to second sensor. So for each sensor, you will provide the graph of plots. With this graph of plots, we'll transform each edge in a vertex in your graph of plots, for example. At this point, you will apply an optimization algorithm called Danzig, and you will have the best paths of each sensor at this moment here. So with this information, you can have again the initial plots that belong to this best path. This algorithm, pair of plots in 2 stages, this first stage you can parallelize. As you will see here, if you have more sensors, you can compute this data related to each sensor in parallel, okay? But until that, we didn't have any parallelization of this algorithm. So when my work was proposed, it was the first attempt to parallelize this algorithm. This is the second stage. This stage we start with the best path of each sensor in separate, and then we will combine the plots here, and again to have a graph of plots until we will have the best path of all of our sensors. This is the main idea of this algorithm. So for our proposed solution, I will not show you any details, but as I told you, my intention here is to give you an overview of the solution. So first of all, we will have some approximations. For example, all of the data received here at this red area, all the plots of this area, we will receive the same timestamp, the same time tag in this case here. For this algorithm, we will need to receive information, real information of 3 points, 3 plots of the real target. With this information, the algorithm calculating kinematics information to be used in all of the graph. Oh yes, this solution is a graph-based solution. So we have some rules to create our edges in the graph, And we have a sliding window here. So at the first step of this algorithm, we need to wait for receiving all of the data of this slide window. For example, the size of slide window is 10 in this case here. In the multiset in Gamma, our data was represented by tuples. You know, Gamma, the implementations that we used in Gamma has some how can I say has some limitations to use. For example, the data we need to have, for example, tuples. And each tuple in this case here is a representation of a tuple as a vertex. So each vertex in our solution has the same characteristics. The first element is ID sensor, ID vertex, X and Y elements, time, and a mark that we use this to mark some elements that already computed, something like this. So here is the vertex representation, but all of the edges in our model will be represented by tuples too. So here we have some details about the best path calculation, the first and second steps, and then the third and the fourth steps. So here we have the source vertex, and our solution has some reactions that remove some undesired edges. In this case here, this red one, and the other, we calculate two in this step, in this first and second steps, the cost of each edge. So we have reactions related to the calculation of these costs. This is the third and fourth steps. And basically we have a set of reactions that remove some edges here. So our set of gamma reactions that reproduce the behavior that pair of plot in two stages is detailed here, is showed here. So the three first reactions removed some edges undesired. So the fourth reaction here, we have the assignment of costs to the valued edges. And here we have a set of reactions that calculating the best path in the graph. Here's some vertex exclusion. Here we will prepare the multiset for the next stage. So we have this. That set of reactions reproduces this from the first stage and from the second one. Here, I will not present now, it's here. Let's come back to the main presentation now. Okay. Before I show you some details related to equivalence between data flow and gamma, I just only show you the code. Alexandre, can you change here again? Yeah, the screen. I will only show you the set of reactions that we produce. Is the best. That's the moment. here I have a code that have 11 sensors, data from 11 sensors, and we have that set of reactions that can reproduce this behavior of pair of plotting 2 stages. Consegue passar? Só vai descendo. Pode descendo devagar que eu vou mostrando. So R1, R2 until R16 are the name of the reactions. In this case, we have a sequential computation, but when I put pipe, we have another experiment with pipe that we can put to run these reactions in parallel. So you can. Yeah. So here we have the data related to sensor 1. Sensor related to data related to sensor 1. We have, as you see here, a set of tuples that represent vertex, edges. You know, this is an experiment that I did in my master, but in the doctorate, for example, all of this data is received for a file and another thing, for example. But my intention here is to show you this, the set of reactions, and take an example. Just a moment, because the scroll is not working here. That's it. For example, the first reaction, R1, we replace 2 tuples with this conditions is fulfilled. The second one, the third one. The fourth, and then. Now you can enter again. My intention here is to put this experiment to run to show you. But these experiments, we use the Senapad at the UFC to run it. It's a cluster that we use in our experiments. So here, the objective is only to show you the syntax of Gamma and these main details. Now let's talk about data flow. Data flow is a parallel computational model too. And here, your program is represented by a graph. In this case, in this graph, all of the vertex has the calculation, the operate that you can compute, for example. And the edges is the data dependency between this vertex, these vertices. So in this model, an operation can be executed when the operands are available. What I mean, if you have a vertex, for example, with 2 input edges, when these 2 input edges are ready, when you have these operands, the operation will execute. In this case, we don't have a program counter. It's different in a sequential proposal as a von Neumann architecture, for example. We have some special vertex to do this possible. In this case here, these square nodes, these square vertices represents data, the input data in this case here. For example, we have here a special vertex, that will be used in selection functions. Here, a logical test, for example, a sum. Data flow is a computational model, parallel computational model, large used. So in 2019, we proposed the equivalence between data flow and gamma. This first work here, we did only some empirical tests. We proposed an algorithm, a conversion algorithm, some basic concept, a study related to reductions. These reductions are techniques to leave your code more simple with less reactions, for example. And here, 2021, we propose a formal equivalence proof. So the basic idea of this equivalence is, if you have a vertex in a data flow graph, you can convert this into a gamma reaction and vice versa. In this way, a data flow graph edge can be transformed in a multiset elements like this. So we have here a simple graph that represents a data flow graph. And the basic idea here is these elements will compose your initial multiset. Each vertex will be transformed into a gamma reaction. This is the main idea behind our study. Now let's talk about some problems to gamma implementations. Because, as I said at the beginning, when we decided to work with gamma, my initial intention was to solve a problem. Basically, to solve a problem that we had at the Brazilian Navy. But now we are using a model, a different model, a parallel model, and we have not many, but some implementations of this paradigm, and we have problem with this. This is the main structure of implementations used by Professor Mulayer, and we have a serious problem with these implementations. I know this is an academic proposal, but for example, we have a serious bottleneck here. This bag cell here is responsible for give the multiset to any reactions. In this structure, all of the worker will be responsible for compute one reaction. So as we see here, we have a bottleneck because when the first reaction is using our multiset, all of these workers is stopped. This is a very a serious problem in this case. This is true in the implementation gamma sequential, gamma MPI. Gamma MPI is the same structure, but the workers run in different cores. It's a unique difference. And the third implementation that we did here, that we propose here at the university, we use the same structure, but the work of the workers, the work that run here at the workers, we put this in the GPU, the only difference. So because of that, because these bottlenecks, the limitations, I proposed G-Sync, as we will see soon. First, I show you G-Flow and G-Sync. This is the basically workflow. We use here an environment developed here at the university for data flow implementations. So the university developed the Quillar that we have, for example, code in C. And we produce data flow code, data flow assembly code here, and we have a complete runtime of data flow here. The Trebuchet and the Quillar propose this. In our case, we propose these left tools. This first tool is a tool that can convert this code in Gamma code. And here we have another environment to run codes that is very, very different. Here we have a real real execution of reactions in parallel. So GFlow is the first conversion tool between data flow and Gamma. So the tool works in this way. We have an assembly code, and we convert this into Gamma code. This was implemented in Python, and we have more details here. But the main idea here is we have an assembly code that represents a data flow graph, and we can convert this into Gamma code. This is the main idea behind this. And now G-Sync is a completely new runtime. Though that structure that we have some workers, we don't use this here. So our proposal here are based in a graph and the edges reversal of sinks. So you have some sinks. Sinks are vertex that all of your edges are input edges. So you identify these sinks, and each sinks in this proposal represents an instance of execution of any reaction. So for all your reactions that you have in your model, you will have some instances. These instances is a selection of elements that can be react in Gamma. So you have a graph, you have sinks, and the algorithm will reversing edges of the sinks and identify another ones and executing in a real parallel way the execution of reactions in this case. This was implemented in C language. We use some details, some characteristics of LEC IAC used in the other implementations of Gamma. Now some conclusions, future perspectives, and more. So in our experiments, we can see that Gamma is suitable paradigm for Brazilian Navy data fusion applications. As said to you, we need some research effort to become Gamma in a powerful tool. We have some problems to solve yet. Is a declarative way to program data flow, because as we can convert a Gamma code into data flow and vice versa, Gamma can be seen as a declarative way to program data flow. We provide the equivalence between these two different paradigms. GFlow was the first conversion tool between Gamma and data flow. G-Sync is implementation of a parallel environment that really can execute reactions in parallel. For future works and some perspectives, we are thinking about applying approximate computing techniques to Gamma. We already done some initial experiments with these techniques, but Gamma is suitable to use this kind of techniques. We use thread in the first proposal of a G-Sync. So now our intention is to propose a distributed multiset in a fully distributed version of sync. these distributed multisets in Gamma, our intention is to exploit locality. Here we have some reference. The first one, we propose G-Sync, the scheduler mechanism, in a CGRA architectures. Here we have equivalence study. Here the fluid computing is using Gamma as architecture for heterogeneous computing. Here we have the initial proposal of the equivalence. Here, a Gamma implementation using the structure proposed by Professor Boulayer, but with the work of workers running in a GPU. Here another reference. The framework, the proposal of a framework here. And here is the proposal of parallelization of that data fusion algorithm that I showed you in a very fast way here. So thank you very much. As I said to you, my intention here is not to show you many details about Gamma. We have a lot of things to show you here, but I think that the first approach here is only to show you Gamma. Is something very different, very different show, very different to see. But we have some good perspectives using this. Today at the Navy, we don't have any work in this area. Pablo has a lot of works using data flow, algorithms, but this proposal Gamma, today we are not working with this today, but it's something that has a good perspectives and possibilities to use, including data fusion algorithms. So if you have any questions.
Thank you. So, any questions? Yes.
Congratulations for your work.
Thank you.
This is very interesting. I was wondering what will be the main limitation that you can see in this perspective. I know it's something that's not fully implemented today. You're studying, but it's very interesting. So what will be the main limitation right now in your area?
So the main limitation, I think, was characteristics of the Gamma implementations. As I told you, Gamma is a formalism. So as an idea, it's very good, but when you have implement this, we have many problems. So I don't told you here, but we had a lot of problems proving the equivalence, for example, because Gamma is a non-deterministic model and data flow is a deterministic model. How can we prove the equivalence between these different models? But in my opinion, today, the first limitation already still is the structure of execution. My proposal of a scheduler has a good possibility to really execute reactions in parallel. But I propose this using threads. So we have some problems, but we can prove. I don't bring here, but I have the results. But in my opinion, this is the main limitation, the characteristics of the implementations. But our results in the doctorate showed that as you can increase the computation in your reaction, in one reaction, we can have speed ups. Because I didn't told here, but I didn't tell here, but the first proposal of Gamma, all of the computation is a unique logic operation, a sum, for example. So we change this, we put, for example, a function inside a reaction, and we have, with my proposal, a very good possibility to have speed up.
Yeah, that's nice. A really good perspective, because that's a natural limit.
Yeah,
It's a natural process. Thank
Yeah.
you.
Any questions? Yes.
Thank you very much. I'm not. It's working? Can you hear me?
Is turn the door?
Yeah.
I'm not familiar with data flow, so thank you for your presentation. It was
Thank
very
you.
nice. I'm not familiar with data flow. It is not clear the difference with gamma. Yeah, it is deterministic, whereas gamma is non-deterministic. But what would be the advantage of using gamma instead of data flow? That's my first question.
Okay. So the difference, I will try to clarify more the difference between these two models. In Gamma, your computation are expressed by a set of reactions. So you have a lot of reactions. In these reactions can execute freely. You don't have you don't have to have, for example, a program counter to show another operation to be executed. All of reactions, if the reaction condition is fulfilled, the reaction will run. This is the main idea behind the Gamma. Data flow, your program is expressed as a graph. So all of the nodes, all of the vertex of this graph is the operation that you can run. But we don't have a program counter too. But the difference is, in the data flow, your data dependency is expressed by edges. So you have a vertex that has, for example, 3 input edges. If all of the 3 input edges are ready, these operands are ready, you can execute. But notice that if you have another vertex that depends on the result produced by another vertex, your program have to wait the production of this data. Is something similar, but the way of you express your problem is different. This is the main idea behind the difference between them. But in Gamma, the choosing elements in Gamma is a non-deterministic thing. In data flow, the determinism of data flow is expressed by your graph, you know?
By the graph.
Yeah.
Yeah. So we skipped the synchronization, and then you got some speed up.
Yeah.
But you lost you lose this determinism.
Yeah.
Okay.
Note, for example, that for approximate computing, your reactions can execute in your Multiset, and you can, for example, stop them and have a good result. Different from the data flow graph, that you need to wait for all of the data dependencies is the operations execute, and at the final you have a result. In Gamma, you can, for example, in a data fusion domain, for example, you can remove some undesired elements and stop your computing anytime you have. Is a good possibility for Gamma. The question that you told now is very, very interesting. Why Gamma and why not data flow?
Yeah, that's the point.
Yeah. Our studies, we show that gamma can be more, can have more good perspectives than the data flow in some application domains. But today, data flow is more usable. For example, we have TensorFlow. Many, I showed here, many companies that use data flow things. We have more studies in data flow. Just the concept here. In Gamma, we have some applications related to image processing, some problems related to the graph. We have some, but really, data flow, we have much more in Ford here.
That's great. Another question regarding your data fusion application. My question is, can you make sure that you can follow several targets with that approach? I mean, I believe you have a lot of plots in multiple scans, and you're trying to create those paths indicating possible targets, possible vessels, whatever. And can you make the distinction between different objects, between different targets with that approach when you run?
As I said to you, I used an algorithm. In that time, were used in Cisne. PPDE was implemented in Cisne by another colleague, Rogério, and the work of Rogério was to divide the algorithm in 2 stages. Only dividing this algorithm in 2 stages, you have the possibility of parallelize the first stage. But this not answer your question. So when I studied about this algorithm to understand, to can prove a set of reactions in Gamma to do this, one characteristic of this algorithm is multi-target, but I didn't study more about this.
Okay, thank you very much.
Thank you.
The algorithm works in a slide window, so maybe that's about his question, right? So there is no possibility because he considered another graph is when the window is sliding across the time.
Yeah, when the slide window is the first stage of the algorithm, we need to wait to complete all the window, and then another data received, you will calculating again the algorithm, the graph of plots, pair of plots. I don't know if this is your question.
Yeah. I would like to take advantage of his first question. If someone is watching or seeing this Gamma thing and data flow, I thought that I ran away off chemistry in the high school, but I'm facing again here. So it's I think people are doubt about. It's about semantics, syntax, or it's related to process scheduling, because we are talking about to use von Neumann architecture, right? So we're not using a native platform to run these algorithms. You are translating, right?
That's it.
A code written in Gamma to a code written in C, right?
Exactly.
So maybe your first question may be, well, how can I take advantage? Because it's not a fair comparison if we make a benchmark using a code written in C, directly in C, right?
Run faster.
Run faster, probably, right? I use something like written using MPI, right? And probably be faster than Gamma, right?
Yeah, yeah.
So I wonder if to perform there is something like on a native platform or hardware and architecture considering the Gamma features. I mean, using this is something that we can discuss.
Okay. So no, we don't have today hardware that can run Gamma in a natural way.
Because you're talking about a program counter and stuff like that, because
Yeah.
it's something in von Neumann architecture, right?
Yeah.
And it's not my thing, so
No problem.
I'm asking something silly.
Yeah, no problem. So we don't have today hardware that can execute directly Gamma, but for example, we have some data flow hardware. So as we can convert Gamma in data flow, we can run it in the data flow hardware, for example. And I didn't understand your first question. You need to know about the chemical chemical metaphor.
Because there is what I understood that it's easy to write a program that naturally is parallel, right? It's a parallel way. But if you don't have, and there is something with chemistry that I didn't get it. Because I don't like chemistry. But okay. But think about that. Well, my main question was about actually the evidence of the results that we can have once we are translate code to run in a von Neumann architecture. That was my main question.
How can do this? Is this?
What's the best results? Why can we make a fair comparison?
Okay. So how can do make a fair comparison? As we need a good implementation of Gamma to do this. Okay. So my proposal with G-Sync, we have a real, as I told, a real execute in parallel. So in one of my experiments, I increase the computational task that will be running in a reaction, and we could compare. But as our implementation, Gamma implementations, doesn't have any good structure to do this, we are already we don't have today a good comparison with other platforms, but Dataflow has this. I'm trying to always said Dataflow and Gamma, because today we can convert this. And in Dataflow results, I don't remember exactly was, but they provided some good experiments and good comparisons between including other parallel computational models. I don't know if Santiago, do you remember the comparison, Santiago? Because Santiago works with me at the master and my doctorate. And Santiago worked with some data flow computational models. And I remember that Marzullo and Thiago, they had good comparisons with data flow, with Trebuchet, with another computational parallel models. Do you remember these results? I know they had, but I don't remember exactly was.
Yes, we have some work that is focused on comparing the data flow performance environment with the von Neumann architecture, but it was running in von Neumann architecture, the data flow solution, right? Not in fact implemented in hardware itself. There are some works that in Brazil, but in the Microsoft, for example, they has a solution called Catapult that they provide some FPGAs implemented in a data flow architecture. The architecture is called the wave scalar architecture. Okay, and then in that catapult project, they have comparisons considering the programming running in the data flow architecture and the von Neumann architecture. Okay, that is one thing we need to adapt to include Gamma implementation as well. It should be a nice work, maybe. So that is what we have.
Thank you, Santiago. I forget to told you here that we are thinking about using Gamma as a computational, as a syntax for quantum computing too. But it's a very, very initial ideas, very, very initial studies.
Any more questions? Yeah. So,
if you have more questions, I can tell you the results of our study. As I told you, is many things to show you in the shorter time, but we have good results, as I said, comparing with another Gamma implementations, not another computational models, but we compare with other Gamma implementations, and especially our scheduler is very, very good results, has very, very good results.
This was G-Sync?
G-Sync, yes, G-Sync. G-Flow is a conversion tool, and G-Sync is a complete parallel environment to execute Gamma programs.
Well, it was very instructive, and I would like to say thank you. Terrific presentation, and that's it.
Thank you very much.
Oi. Vamos fazer coffee break 10 minutos y voltamos. ¿Sí? Just a short coffee break for 10 minutes and we come back.
Alô, alô. Assim tá ótimo? Ok.
Perceba.
Como é que eu fecho isso?
Se eu pegar o microfone e botar aqui, ninguém vai escutar. Aqui também não. Aqui também não. Aqui vai escutar normalmente. Dessa posição.
Bem direcionado.
Bem direcional. Unidirecional.
Tá joia.
Então, por isso que hoje repórter na rua usa esse tipo de microfone.
Pra ficar.
Para ficar aqui para não pegar o ambiente.
Tá bom, tá joia. Pode deixar.
Só isso. Pode usar um mouse.
Vou apresentar você, passo o microfone e você faz. So, can I go? We're going to have our next tutorial, but before this, I would like to introduce Professor Aldo from Federal University of Goiás. He's a colleague helping us to the arrangements of this conference. So thank you very much. And
Hi. The next talk is a tutorial entitled Cooperative Localization and Distributed Target Tracking in GNSS-Denied Environments using Factor Graphs. And the speaker is Steven Schwanz Diaz. He received the bachelor's in computer engineering from the Federal University of Espírito Santo in Vitoria, 2006. The master's in ITA, San Jose dos Campos in 2008, and the PhD in electrical and computer engineering from ITA as well in 2014. His main research interests include distributed estimation in sensor networks, Bayesian inference, and machine learning. Dr. Diaz has been with Eindhoven University of Technology since September 2021 as a machine learning lecturer, where he has supervised several graduation projects mainly focused on anomaly detection and prediction applications. From 2008 through 2021, Dr. Diaz worked for Embraer Group as a system engineer specialist, designing coastal surveillance applications, and as a researcher engineer, developing advanced data fusion systems for embedded command and control, C2 systems. Since February 2023, Dr. Diaz has rejoined Embraer as a data fusion research engineer and lead R&D projects. So let's welcome Professor Steven.
Okay, thank you very much for the introduction. Okay, so I'm Steven. I'm with Embraer and with the Eindhoven University of Technology. Okay, and today I'll present this tutorial. This tutorial is based on a PhD thesis from one of our students, Alison. This work was executed at ITA, the Aeronautical Institute of Technology, the Brazilian one. And okay, Marcelo Bruno was his supervisor, and I was his co-supervisor, okay, during this PhD. And so this is not exactly my work, is the work of one of our students. And I'll try to present some of his main results today, but I need to provide a lot of background, so be patient. To understand his main results, I need to do a lot of math today, okay? The work is about cooperative localization, distributed target tracking. More broadly speaking, I'm going to present how to perform inference on graphs, okay, using this framework, the factor graph framework. Good? By the way, you can interrupt me anytime if you have any question. It's okay. That's the outline, the agenda for today. There's a brief introduction, then the theoretical background. It is required. I'll try to explain two applications today. I'm not sure if you have the time. The cooperative terrain-aided navigation using factor graphs, and then the joint cooperative TAN, terrain-aided navigation, with distributed target tracking, with a single target. Okay? And then some conclusions. Good. Let's go to the introduction. Those are the learning goals for today. Some principles, some theoretical background on Bayesian filtering. I think this is very interesting to be able to follow the proposed approach. And factor graphs as a modeling tool. Okay, so factor graphs are a very convenient modeling tool for distributed estimation tasks. And then the belief propagation, also known as sum product algorithm, which is the inference engine that you run over the factor graphs. And finally, I'll try to apply those, at least for one of those applications. If you have the time, I like to cover both applications today. So why using distributed estimation? Why not just forwarding everything to a data fusion center and processing everything together? Because this is the best approach in terms of optimality. The best thing you can do is to forward all information, all sensor information, to a data fusion to process this data together and produce the estimates. But in several applications, engineering applications, you have multi-agent systems. Those multi-agent systems, the agents have some processing, sensing, and communication capabilities, and they need to cooperate together to perform some task. Okay, here you have one application. Sorry, it's a man-and teaming. In this case, here is a loyal wingman. So there's a manned aircraft, this one, and several drones that are acting like a loyal wingman to, for instance, to protect the leader, to combat, to engage the threats in the air combat scenario. Okay, but to be able to cooperate, they need to solve some very basic problems. They need to, for instance, to localize themselves. They need to know where those agents, their cooperative agents are. And they also know to track the threats, the targets, okay? So this is very important. Those are very basic inference tasks they need to perform before thinking about cooperating, thinking about distributed decision-making, whatever. They need to know, they need to increase their situation awareness. So this kind of inference tasks that we're going to focus today. Good. And another task, another example here is from one of our collaborators at ITA. This is a very interesting scenario in which several drones, a drone swarm, and by the way, this is a simulated scenario, as you can see. So you have a drone swarm of drones. They are cooperating to protect some area. So here we have a protected area here, and the drones, they are cooperating to engage and disable some kamikaze drones, some threats that are trying to reach, to hit your protected area, okay? And this is the same thing. They need to localize themselves even more. They need to navigate, to know their full navigation state, position, attitude, and so forth, to be able to control the formation, for instance, to keep a combat formation, to engage the kamikaze drones, disable them, and protect the area. And they also need to track the kamikaze drones. So cooperative localization and tracking is a very important task in this kind of scenarios. Good? Any questions so far? It's okay to interrupt. In our particular scenario that I'll present today, you're going to explore a multi-agent systems, several aircraft. They are flying together in some formation, and they are in this scenario, there are no GNSS. So they are in a GNSS-denied environment. Perhaps someone is spoofing or jamming the GNSS, the GPS signal. So you cannot rely on GNSS to localize yourself, to globally localize yourself. Good? And usually we rely on GNSS. That's the point. And furthermore, they need to track objects. Usually use radars to track other objects, but to be able to properly use this signal, the radar detection, to track another object, you need to localize yourself, because the observation itself, it's a relative distance and azimuth. So you need a good location, self-localization to do tracking as well. So those two problems are kind of entangled. They affect each other. That's what I meant. And in our approach, each sensor, each agent, they collect multiple local observations. Okay, so somehow they measure the global position. In our case, you're using TAN. You're using the terrain information to globally localize the agents. And each agent is able to do that, to perform TAN solely. Good. And they cooperate through message passing. So they need to exchange messages through a network, some network infrastructure to be able to cooperate. So the network infrastructure is very important to enable this cooperation. And they do that for both localization and tracking. Okay, centralized solution would be the best idea here, but in a multi-agent system, that's not a possibility. You cannot forward all information to a central data fusion. In our work, you're going to use the terrain-aided navigation as a source of global positioning. So I'll show you how to perform that. Okay. And you're going to explore factor graphs as a modeling tool and the sum product algorithm, the belief propagation, as a mean to do inference on graphs. And you're going to solve also, this is our first paper for the transactions of our aerospace. And there's another paper it is a result from this thesis. You're performing also the joint cooperative localization and tracking, okay? That's our second paper. And there's another paper, it's a conference paper for ICASP. It's a conference in signal processing. And in this case, you also consider dynamic factor graphs. I'll explain later what that means. Those are the references from our work, the two transactions on aerospace journal papers, the ICASP. And this paper here is very interesting. Describe that scenario with drone swarms. So if very interesting, you can have a look here to understand how they solve that problem. So I hope that you have some coffee. There is a lot of math. Those slides were the last nice figures from this presentation, so don't be scared. Let's start with some general concepts. The first one is filtering. How you do filtering using the Bayesian approach. Okay, this is very important. Usually, people talk about Kalman filtering, extended Kalman filtering, unscented Kalman filtering. But the first thing you need to do to know actually is the Bayes filtering. It's the basic filter, more general filter, and all those filters actually are particular case for the Bayes filter. Let's consider first this very general model. So let's say X here denotes, it's a random vector, it denotes it's a model of your hidden state. So for instance, your location or the target state, position, and velocity, okay? And this model here describes, it is a dynamic model, a probabilistic dynamic model describing how the current state is related to the next state. In this case, we're using, for simplicity, here considering just discrete time model, okay, for simplicity. Could be, this is more simple to explain. So this function here is possibly nonlinear, okay, and it's a deterministic part of this model. I can use here perhaps, yeah, that's more convenient for the online audience. Good, so this is our deterministic model relating the current state with the next one. And this is some noise. It models some perturbation, something, our uncertainty regarding how the state evolves through time, okay? And this disturbance, this noise, it follows some distribution, this distribution here. Okay? So far, so good. Okay. This is a sequence of hidden states. So we do not have access directly to this sequence of states. You somehow need to observe this sequence. And so we have another model here describing how the observations are generated from this sequence. It is relating our observation, for instance, a radar measuring the distance in azimuth to the target, with the true target state. So we need a model describing this relationship, and it is a probabilistic model. So we have on the observation noise here, following some distribution, possibly non-Gaussian, as well, relating those two quantities, those two random vectors. Good. And what is our goal with Bayesian filtering? To provide an estimate of this hidden state. We do not have access directly to it, but through the measurements, you like to produce an estimate of this hidden state. So for a continuous value hidden state, you can compute, for instance, the minimum mean square error estimate, which is this expected value here. The expected value of the true state given all observations up to that instance. So you need to solve this integral here. And guess what? To solve this integral, we need to propagate what you call a belief. You can call it a belief, but actually it's a posterior distribution of the state given all observation up to that point. Good. So that's what the filtering does. This is what you need to do. The Kalman filtering, at the end of the day, is propagating this belief. It's a Gaussian belief, as you see later. Good. Under some common assumptions, very nice assumptions, you can say that the next state does not depend on anything else besides the current state, okay, or the previous state in this case. This is the first order Markovian assumption, and that the current observation just depends on the current state. That is, the observations are independent through time, over time. In this case, you have this Markov model, hidden Markov model. Everything here above, this dashed line is hidden. You do not have access directly to it. And this is the Markov process. And you have a sequence here of random states, and they are related through this state transition distribution. So that's our dynamic model. Actually, those equations before, they induce this distribution. And the same thing here, the observation model, that equation, this new distribution here that relates our hidden state at each time step with our observation, okay? That's good. If you have questions, please raise your hands. That's okay. I'm going very slowly. The Bayes filter, on the other hand, it's a means to propagate this posterior through time. That's what you need to compute. You need to propagate this posterior. It's a distribution of the state given all observations so far. That's the job, the Bayes filter job. Usually, you break the Bayes filter into two steps, the prediction step and correction step. So we start with this posterior at instant n-1, and recursively compute a new posterior at the next time step. But usually, we start with this previous posterior, computes a predicted posterior. Okay, this is a prediction step. And then you use the observation here to update, to do the correction, and compute the updated posterior. Good. And this is a prediction step. I'll try to summarize here the Bayes filter equations, okay? Those are the more general equations for Bayesian filtering. Actually, there's under these hypotheses, under the first order Markovian, you can write this step, the prediction step, using this integral here. So here, you're relating the previous posterior with the predicted one. And to compute this predicted posterior, you need to solve this integral, which is the Chapman-Kolmogorov equation. So yeah, you need to integrate over the entire state space. This is not an easy task. Usually, you don't have a closed formal solution to this task. So that's why you need to use some approximations to be able to compute this prediction step nicely. And the Kalman filtering, it's very nice since there is a closed formal solution when everything is Gaussian. You'll see it later. And for the correction step, you're computing here the predicted posterior. From the predicted posterior, you're computing the updated one using the observation model. Okay, this is exactly the Bayes rule. That's the main, everything about Bayesian, actually, it comes from the use of this rule as a means to incorporate information containing in the observations. To be able to get the observation at that point, actually, YN here is the current observation. To get this information, the observation, and plug the information in this observation in the posterior, updated posterior, you need to use the Bayes rule. Okay, that's the how we plug the new information in the posterior. And just an observation here, this is a distribution, but when you plug here the observation, you got a likelihood function, actually. It tells you how likely is to find the state, the true state in the state space, given that observation, that particular observation. So that's why we express this information and plug it into the updated posterior. Is that okay? Okay, when we have this linear Gaussian signal model, so the dynamic model is linear Gaussian. That's very nice. So linear, and the noise is a Gaussian distribution, zero mean Gaussian distribution with covariance matrix key n. And here, the observation model is also linear and Gaussian. The noise, observation noise, follows the zero mean Gaussian distribution with covariance matrix R. In this case, those are the induced distributions for the observation model, for the dynamic model and the observation model. So everything is still Gaussian, okay? And you have, okay, this is a Gaussian, multivariate Gaussian if you're not familiar with, but in this case, those equations, they are the Chapman-Kolmogorov equation and the Bayes rule, they have a closed form solution. So this is the optimal solution to this problem is the Kalman filter, as I mentioned before. All the posteriors are Gaussian and just need to propagate the parameters, the mean, vector, and covariance matrix of the Gaussian distribution. This is the prediction step, okay? So the predicted posterior is also Gaussian with new parameters here, the mean vector, which is basically the deterministic extrapolation of the previous vector, mean vector, and the new covariance matrix. And just to skip this part, this is the update step, the correction step. You have also a new Gaussian distribution with those new parameters here. This is the innovation or residual, the difference between the actual observation and the predicted one. This is the covariance of the residual. This is the Kalman gain, the gain of the Kalman filter. And this is the updated mean vector. And this is really nice for the Kalman filter. This mean vector, this parameter of this distribution is exactly the MMSE estimate, is the solution that you're looking for. Okay? So let's skip this part. Okay, there are several implementations of the Bayes filter. It depends on the if you offer a model, it's a linear or nonlinear model. Depends on the distribution of the noise. But there is a very interesting approach. We call it particle filtering or sequential Monte Carlo. In this case, we use different representations for the posterior. You use a Monte Carlo representation for the posterior. That solution, okay, let's start with perfect Monte Carlo. There is a very nice result. It is the law of large numbers. In this case, you can approximate that estimate, the minimum mean square estimate, by a weighted sum of particles. Okay, this is as far as you can draw generate samples from the true distribution, this true joint distribution of the entire state sequence. If you're able to generate samples from here, you can approximate this expected value like this. So you can compute the MMSE estimate. It converts to the exact solution if you use a very unbounded number of particles, of samples, okay? So it is optimal, it is sense, but it has a drawback. Usually, you're not able to draw samples from here. So usually that's not possible. You need to resort to some alternative to be able to generate those samples. That's what it means. Okay, since you're not able to generate samples from that, directly from that distribution, the true distribution, we need some alternative. In this case, you generate samples from a proposal distribution, a more convenient distribution that you can somehow sample from it. Sample is how we generate samples, draw individual realizations of the distribution. Not sure if it is clear, but those are the particles, are also referred as the particles. So we select an alternative distribution. I call it P here, this distribution here. Oh, sorry. Right hand is better. Okay, we select this alternative distribution. It's called a proposal distribution. Draw a sample from there. Okay, it is an entire sequence of states, and then plug the last state here in this equation to compute the estimate, the minimum mean square estimate. And then we adjust the weights using this ratio here between the true distribution and the proposed one. The funny thing here is that usually you can compute this ratio here even if you're not able to draw samples from it. I'll show you how. And okay, but here you still need to generate samples from the entire trajectory. There's an alternative, is to do sequential importance sampling. In this case, instead of generating samples for the entire trajectory, you can generate samples recursively, okay, at each timestamp. And this is the SIS algorithm, the sequential importance sampling algorithm. It's a very naive algorithm in this case. Since there is no resampling, it suffers with several limitations, okay? I'll not give you details at this point, but just to summarize, we draw a lot of samples recursively at each timestamp. So this is the one iteration of the filter. We start here with some weighted particles, a representation of the posterior given by these weighted particles, and the output is a new representation. It's a new particles, okay, with the updated, representing the updated posterior. So we start drawing a new sample at a given state, a given instant, from this proposal, update the trajectory, so you're forming those trajectories on the fly, and then update the posterior, the weights of those particles like this. You use, look, you're using here the ratio between the likelihood function, this is the likelihood function, this is the state transition distribution, and the proposal distribution. So we need to plug everything here together to compute the new weights. And then you just need to normalize all weights to make sure they sum up to 1. This is the overall particle filtering, a very naive algorithm that doesn't care about resampling, some important steps that you need to take care to not broke your filter, okay? Just to illustrate the concept here of sequential Monte Carlo, because this is important for what comes next. Okay, so you can do sequential importance sampling. And okay, if you choose this proposal distribution here as the, oh, sorry, there's a -1 here. If you choose this proposal distribution as the state transition distribution, so the filter gets very similar to the, for instance, the base filter. So we have a prediction step. You move the particles according to the state transition distribution. Okay, then you update the particles using the likelihood function. That's the prediction step and the update step, similar to that. Okay, and afterwards you just need to normalize everything, the weights, so that they sum up to 1. Good. This is very basic introduction to particle filtering. And this algorithm here is naive. It does not resample particles, and it is blind in the sense that the proposal distribution doesn't care about the observation. It is not seeing the observation to move the particles. We're just using the state transition. The particles are just moving according to state transition. Good. And this is the Monte Carlo representation. I've skipped this slide, but I'm just summarizing here, just a remark. Instead of representing our posteriors as Gaussians or anything else, you're representing them as a Monte Carlo representation here. Okay, it's a weighted sum of Kronecker deltas. Okay, several pews with weights according to each particle. Okay, that's our representation for alternative representation. It is a very flexible representation in the sense that you can, the true posterior can be anything. It can be a Gaussian, can be a multimodal distribution with several peaks, to say. And so it is very flexible, but usually we need a lot of particles to be able to nicely propagate the posterior. So let's talk about factor graphs. Factor graphs are probabilistic graphical models. Okay, it's a way to represent our distributed estimation task. It denotes a factorization. We have some global function, let's say f here, with nv variables. Okay, x1 through xnv are variables that are arguments of this function, and you like to factorize as a product of several local functions, factors. You call these functions factors. And those local functions are the arguments of those local functions are some subset of those variables. Okay, let's see an example here. Okay, before the example, some definitions. The factor graph is an undirected graph, so the orientation of the edges doesn't matter at all. Okay, and there are two types of nodes: variable nodes and factor nodes. Variable nodes represent those variables, x1 through x and v. And the factor nodes, they represent the local functions, the factors, some relationship between those variables. Good. And the adds, they are always between variables and factors. There is no adds between two variable nodes or between two factor nodes. Any questions? Okay. Let's see an example here. So we have this function here, this global function with 5 variables, okay? And we have 5 factors as well. So they have different arguments. They have different subsets of those variables as arguments. And this is the corresponding factor graph, okay? So factor phi A is linked just to this variable. Factor B is also just to this factor here. In factor C, just to illustrate, is linked to 3 variable nodes. Okay, that's the presentation. But why this is important? How this helps us to model some distributed estimation task, distributed inference task. This graph, first of all, this graph does not represent the network topology. It's a different thing. Network topology is a different graph. This graph just expresses the factorization and the relationship between those variables. But when you express your model like this, you can allocate those variables at different network locations. Okay? If you have a multi-agent system, some of those variables are at different agents, should be processed at different agents. So that's why it helped us to model the problem. And there's another advantage. We can see which edges cross our internode edges. I mean, are linking nodes at different natural locations. That's what I mean. So some of those adds are linking nodes or factors that are at different natural locations. So you can design the message over those adds to fit your network limitations, your network bandwidth. Sure, please go ahead. The factors are also located at different natural locations. You should design which factors will be at each natural location. Actually, you need to pay attention on, let me show you here another slide. Okay, you should see later, but you need to take care which messages are supposed to be sent, to be exchanged over the network. And then you should use approximations to limit the network bandwidth. In this case here, we're not that concerned with processing limitations at each network location of each agent, but you need to reduce the communication burden. You need to reduce the number of messages, and you need to simplify those messages to reduce the communication cost. So some of those nodes, factors and variable nodes, they will be at one natural location. Some of them will be at another one. And there are messages. There are 2 types of messages, from a variable node to a factor node and vice versa. There's from factor to variable node. So let's see an example soon. Is that clear, Gomes? Good. Let's see. The belief propagation, or also known as sum product algorithm, SPA for short, is the inference engine. That's why we do inference over a factor graph. And you need to design a message passing scheme. This message passing, it's what unlocks, enables the cooperation. Okay, there are two types of graphs: the tree structured. This is more easy in the sense that there are no loops. Okay, there aren't loops. In this case, the belief propagation yields the exact computation, the exact posteriors at each node. And there are loopy graphs, cyclic graphs. In this case, you need to do some approximations to converge. It does not yield the exact marginal posterior at each node. When I call marginal posterior, I mean the marginal posterior of this variable node. Okay, that's what we're looking for. And the two types of messages, from a factor to a variable, that's our notation. Me, it's a message, and the subscript here it means that is from a factor phi to a variable x. And okay, you got the idea here. That's the variable, a message from variable x to a factor phi. The orientation here matters a lot. Okay, the graph is not directed, but the message, they have some direction, an origin and destination. And let's see very quickly the sum product algorithm. You need to compute those masses. That's the sum product. There is you need to design those masses and compute them. Okay, this is a message from a factor to a variable node. It seems very hard to compute, but let's just try to explain here graphically instead of looking to this equation. To compute this message here, the outcome message from a factor phi to a variable xj, you need to take the product of all incoming messages from variables. So this factor is just connected to variable nodes. So we need to take the product of all those incoming messages, multiply by the factor itself, okay, and compute this multiple integral. Okay, that's not easy. So you need to resort to some approximation to be able to compute those integrals, okay? And here it is the other type of message. So a message from a variable to a factor. In this case, you need to compute just the product of the incoming message, okay, from other factors, as you see here. It is a bit more easy to compute. It's just the product of those messages. This is basically the sum product algorithm. As you compute those messages and propagate them over the factor graph, you're able to compute the beliefs, to propagate the beliefs over time. Okay, let's consider one example just to illustrate how these things works. How many time I have? Sorry? 20 more? Wow, so, okay, that's a challenge. Challenge accepted. Okay, sequential Bayesian estimation. Let's see how to use this to perform inference on the HMM model. So we have this is how you compute the joint posterior given the prior distribution. The model itself, the state transition, the distribution, and the likelihood function. Okay, this is the graph. Okay, induced by this equation. This is a factorization, right? So you're going to compute this factor, this joint distribution. This is our factorization, and I'm just expressing this factorization here as a factor graph. So we start from this factor, which is the prior distribution, and this is our hidden Markov model expressed as a factor graph. And those are the masses that I need to compute, okay? And those factor here, those are used they are related to our observations, and they are used to assimilate observations, okay, from our sensor, for instance. Okay. Sorry, just a second. Okay. And if you use the sum product algorithm here to get, okay, now it's there. If you use this sum product algorithm, that algorithm to compute the messages and propagate over time, so on forward propagation of those messages over this graph, you got this expression here for each node, for each message here. So the message here from this factor to this, actually from the previous factor here to this, let me see. Oh, sorry, from this factor to this node, sorry, is given by this expression, which is exactly the Chapman-Kolmogorov equation for the base filter. So for this particular graph, this sum product algorithm, it collapses to the, it's exactly equivalent to the base filter, okay? So in this case here, this equation is just the prediction step of the base filter, okay? And finally, the next step here, so I just focusing here in one step, and the next step here, the new message, from this node to the next factor graph, okay, is exactly the base rule, okay? This is, so by performing the sum product algorithm over this graph, it is equivalent to do the base filter over the equivalent JM, the corresponding HMM. Good. Let's skip some slides. This is the prior. Let's skip and do the cooperative terrain aided navigation because we are running out of time. Let's see one example here. So that's our problem. We have several aircraft, 12 aircraft flying over a region, okay? And they are cooperating to localize themselves. So they need to localize them. And they are under a GNSS-denied environment. They cannot rely on GPS to localize them themselves. But they can cooperate. They can exchange messages and to help them to find their locations. In our scenario, using terrain-aided navigation. So they are flying information, okay, it's a GNSS-denied environment, but they are using the terrain to localize as a global source of positioning, okay? And how they do that? They have some barometric altitude. They measure this information, how high they are, and they also measure through a radar altimeter the ground clearance, the distance to the terrain, okay, this ground clearance. And they have some digital elevation map. They have a model of the terrain elevation, okay? The dynamic model is very simple in this case. The state space is just the positions of each node R. So the next state is just the previous state plus a displacement here. This displacement is computed by an inertial system, inertial navigation system, okay? So here they are just that happening here using the inertial system. Let's suppose those aircraft, they have a fairly nice inertial navigation system. It has some drift, but to correct those drifts, instead of using the GNSS, you're using the terrain elevation, okay? And our observation model, there are two types of observations. This observation here is the ground clearance. So you're observing, relating the hidden state with the ground clearance. And you have this elevation map here. M is elevation map of a digital elevation model of the terrain beneath the aircraft. And you have, this is really important, you have somehow need to relate variables, the hidden states at different natural locations. So for that, you have this function, okay, each aircraft measures the distance to other aircraft, to the surrounding aircraft. This is a partially connected network, and they are using somehow they measure the distance to the surrounding, the nearby aircraft, for instance, using the radio. They can measure the time of flight or the time difference of arrival of their exchanged message, to also observe the distance to the neighborhood, to the aircraft in their neighborhood. They should, the radios should be previously synchronized to be able to do that. But that's one mean to, this is a simulated scenario, but that's just one mean to achieve this result, to measure, to get some distance observation, measurement of the surrounding aircraft, of the nearby aircraft. Okay? Let's run for a while. So that's the goal, to estimate, to provide at each natural location an estimate of their position given the available reservation over the entire network. I'll skip the equations here just to be more, to meet the time requirements. That's our factor graph for this problem, okay? So I just expressing here this dashed box. It's one node, node R, and this is another node S in its vicinity, okay? Here, this graph here is just expressing the hidden state at that network location. So this is the location, I'm modeling here the location of node R. And this is the location of node S at time instant n. So this graph is actually growing, evolving over time, okay? It's replicated here in both directions. Good? And those are the messages. So we need to design those messages. The dashed line messages here, they are exchanged between the neighbor nodes. So those messages, you need to carefully design them to reduce the communication burden. The other messages, are local messages. So this blue message here in those ones, they are local messages. You don't need to exchange them between the nodes R and S. Good. Let's see the prediction factor. This is the first factor. Basically, this is our model, okay? Our dynamic model, how relating the previous state with the current state. This is the local message computed from this previous belief. This is the previous belief, this message here, the previous belief of this state, the location of node R, and then you compute this predicted belief. That's the message alpha. And this is the hybrid GMM SMC implementation. So to be able to propagate over time, we start with a GMM representation of this belief. And since our model is linear Gaussian, the new belief is still a GMM, a Gaussian mixture model representation, okay? And that's our approximation to this message. It is a new Gaussian GMM model, okay? This is basically the Kalman filter equations, the prediction step of the Kalman filter for each model. Great, so this is the TAN, the terrain aided navigation factor. Basically, it's just a likelihood function. I just plug in here the likelihood function of this node from this factor. The message is the same thing. There is no incoming message here, so the product will be just this factor itself. The approximation is a bit more complicated. In this case, since this is a very nonlinear model, you need to sample to convert our Gaussian representation into a Monte Carlo representation with particles, a weighted sum of particles, okay? And then plug this representation, okay, into the likelihood function to update, to compute new weights. So we start here as a GMM approximation, sample a lot of particles, and then after this step, you get a new Monte Carlo representation, an alternative Monte Carlo representation with weighted particles, okay? According to this likelihood of each particle. So yeah, it's a bit processing demanding, this step. And that's the cooperation. Let's see the cooperation. There are two types of message. This local message here, an incoming message from the remaining nodes, the nodes in the vicinity of node R, and there are messages from node R to the nodes in its vicinity. This is the factor, H. This is basically joint likelihood function of all distance observations available at that node to its neighbor nodes. And we start by broadcasting. This is this gamma lambda actually lambda message here is directed to each. It's the same message, sorry, but we broadcast this message to all neighbor nodes. Okay. So this is an iterative process. At the first iteration, the incoming message is just alpha and beta here. But at the next iterations, this lambda message must take into account also this KC message here, this incoming message here. So for the first iteration, okay, it's just the product between alpha and beta. And for the next iterations, we also need to take into account this message from the remote nodes. Okay, this is the Monte Carlo approximation. So let's see here, why using GMM and SMC, a hybrid approach? Instead of sending all particles through the network, that would be very, very costly. The communication burden will be very high. We approximate again the belief at this node by a GMM and send here, broadcast the parameters of this GMM to the remaining nodes. So this is more convenient, okay? It saves a lot of communication bandwidth. And then when those particles arrive at the node S, for instance, at the other nodes, we draw again a lot of particles to assimilate information here, actually to compute this message here. Okay, and let's see now the last message. Please keep with me. Okay, the last message here, you should compute this incoming message here. So we broadcast the information to the remaining nodes, and now we get information from the nodes in its vicinity. With respect to node R, okay? So in this case, you should take all incoming messages here from the neighbor nodes and compute this message here, zeta, or C. I'm sorry, I forgot this letter. You need to compute this message here. Okay, so that's expression here is basically how you should compute this message. Okay, this is a local message, but those incoming messages, they are GMM. Remember, they are GMM, so you need to draw new samples from this GMM and then plug into this factor to compute, to approximate this integral here. So it is a lot of communication board at each network node, but the communication bandwidth, our focus is to reduce the communication bandwidth. And this is the implementation, okay? So we start with this representation of this incoming message, and you plug here in that expression to compute, I'll skip those steps, to compute the outgoing message here. So this message, actually, you have a Monte Carlo approximation to this message, okay? This message is represented by a weighted sum of particles. And here, we're just computing those particles, okay? I won't enter into details here. Without cooperation, so there are some difference here. If you do just one iteration of this step, so there is no cooperation at all, the outgoing message, the final message here is just this product here, alpha and beta. If you do more iterations, at least one iteration, then this message will take into account the information, incoming information for nodes in its vicinity. So there is cooperation in this case. So this is we should run this as since this is a loop effector graph, you need to run this several times, several iterations. And if you don't have this information, the terrain information, you're only doing that reckoning. So the gamma fact message here is just the alpha message. So you're just doing that reckoning. Those are particular cases. Let's see the results. Okay, this is the hybrid implementation, GMM SMEC implementation of this message. Let's skip. So at the end of the day, you have a set of particles, and you use those particles for this message, for this final message, to compute your MMSE estimate. That's the final goal, okay? And this is your estimate, and you have a different estimate at each network location through this cooperation. Good. And let's see the experiments. So we have 12 aircraft. They are maneuvering. They are doing coordinate turn. You're using a sampling period of 1 second. The trajectories are 600 seconds length. Okay. This is a real map of the Brazil, South Brazil. Okay. And it's a 30 meters by 30 meters digital elevation map. It's a fair resolution, but you need to do some interpolation to collect, to plug this map into our model, or our observation model. It is the region here is 54 kilometers by 58 kilometers. It's a fairly huge region scenario. You have experienced several scenarios, several combinations, everyone performing 10, cooperating, some of them just doing that hackoning while the other aircraft are performing 10. That is, some of them are able to perform, to measure the ground clearance, some of them aren't. So we have design experiments with all those combinations to understand if even with few of them are able to measure the ground clearance, to use the digital elevation map to localize themselves. If the remaining ones are not able to do that, are still able to localize through cooperation, okay? And that's some technologies regarding our simulations. I'll skip that. Okay, nice thing. You have made experiments with different GMMs using 3, 2, 1 Gaussian modes. And the results have shown that a single Gaussian is enough. So if you're able to run with a single Gaussian for this particular scenario, this is enough. That's a good news. So you save a lot of communication bandwidth since you're transmitting just one Gaussian through the network. Good. Those are our performance metrics. You're basically computing the error over time for each network location. R here is the network location, and the agent itself, and is the timestamp. And here you're just averaging out over all network locations, but it's still one time step. You're still computing for each time step. That's what I mean. And here it's a metric for the whole scenario. You average out over all network locations and all timestamps. Some results. This is the non-cooperative scenario. So in this case, there's no cooperation. Let's see here. Let's interpret those results. Here, everyone, okay, this dashed line here is the lower bound. It's the best you can do in this case. Without cooperation, this is the best you can do, okay? By performing cooperation, by not performing cooperation, but just doing the TAN, the terrain-aided navigation, all aircraft in this scenario were able to localize themselves. So there's some latency here to converge, but at some point they are able to localize themselves without cooperation. That's good news. So the TAN approach, it's a suitable way to, if you don't have GNSS access to GPS, you can use TAN to localize yourself. But the information, the terrain should be informative. You should, if you're flying over a flat surface, so there's no information there, so you won't be able to localize yourself. But here in this particular scenario, the 12 aircraft were able to localize here. Nice. There's some delay, 100 seconds, but it's fair. But when there's no cooperation, in this case here, just some of them were able, I'm averaging out over the aircraft, so some of them were able, 6 of them, and here 4 of them. So the results becomes really bad. Because those aircraft here, just doing that hacking, just relying on their extrapolation of the inertial system to estimate their positions, they are diverging, they are drifting, and they are getting lost. Okay, that's why this metric here is constantly increasing. Okay, so no cooperation is not that bad if everyone is doing 10. Okay, you have experiment also the number of Gaussians. So just one Gaussian, it's okay. That's a good news. But we also have made different experiments, run different experiments with different number of iterations. So 0 iterations, no cooperation. That's our previous scenario. 1 iteration, that loop, there's a loop, so we need to run several iterations. But we have notes that just 1 iteration is enough for the algorithm to fairly converge. Okay, almost there. 15 minutes. Okay, 15 minutes. Please don't sleep. And okay, so 1 iteration is enough. There's no gain with further iterations. And so 2, 3, there's no real gain here. So let's keep just 1 iteration. That saves also a lot of communication bandwidth, since you just need to send 1 Gaussian for each of those masters, and just once. That's good. So that's further reduce our communication cost. And finally, this is the overall results. Take into account cooperation. Okay, so let's see the most interesting case here. This is the 12 with no cooperation. Okay, that's the previous result. And the lower bound, the dashed line here, the previous lower bound. Okay, I'm just plotting here the previous result as a mean to compare. And here, when you add cooperation, okay, let's see the same scenario with cooperation. Everyone performing 10 with cooperation. That's the lower bound, the PCRLB. It's a Kramer-Hall, posterior Kramer-Hall level bound. Let's skip these technicalities, but this is the best we can do. And the best we can do here is it's on the bottom here with 12 aircraft performing 10. And the blue line here, the continuous blue line here is our result with this scenario. Okay, 12 aircraft cooperating and performing 10. And as we reduce the number of aircraft performing 10, the results get very similar. That's really nice. So the results are not that different here. At least in the steady state, they are very similar. Not that far from the optimum here, the lower bound, but they are very similar. The point is, with more aircraft performing 10, they converge very faster, okay? They converge faster. With less aircraft performing 10, the information must, how can I say, spread over the network so that the aircraft not performing 10 localize themselves. That's why it takes a while here in this scenario with this yellow curve here. There are just 4 aircraft performing 10, and the remaining ones are just daddy reckoning. I mean, they are not performing 10, so they must rely on the information coming from the network. So that's why it takes a while here to converge, but still they are able to localize themselves by means of cooperation. Okay. So I'll skip this section. This section here, I'm supposed to show you how to do also target tracking. Okay, I can share the slides with you later. I'll just show you here the final result. A video showing the final result of this algorithm. Let's just switch. Okay, this is the video. Okay, like before running it, let me explain. So here it's a gut view. So you see the scenario from the above. Okay, those are the collaborative aircraft. Each of those really tiny nodes here are the collaborative aircraft. The ads here, those, I'm not sure about this. It is red. Okay, this color here represents the connections between neighboring aircraft. So those 2 aircraft are able to exchange messages. And this one here is the target. So at this point, just this aircraft is able to detect, it's a radar observation, to detect this target and estimate the distance and azimuth to that target, okay? And the network topology here is changing over time. As the aircraft moves, some of them gets connected from each other, and some of them you'll be able to detect. So the detect, just the aircraft close to the target, you'll be able to detect this target. But even though this aircraft here, which is very far from the target, not seeing directly the target, will be able to estimate its position. Okay, this is just a lateral view. Okay, this is the XY plane. This is the XZ plane. So you can see all the entities from the side. Okay, and so this is altitude of the entities. And here you can see the particles. I mix in here several particles. Each color here represents the particles at a different network location. So let's see, the blue particles here, the light blue particles are actually from this network location. Okay, and initially they are very spread. There is no consensus. They are spread. They are not representing the same location. Okay, this is a particle representation of the target position. Okay, from the top, from the XY plane. So they are spread over the XY plane, and here the XZ plane. This is the altitude of the target versus its X position. Good. So initially they are very spread. Since the nodes are just started simulation in the nodes, they have some prior. This is the prior at each natural location. They do not agree on where the target is exactly. And let's play. Okay. All entities are, okay, now I slow down this, but all entities are moving, the target is moving, the natural locations, ads are changing over time. These blue lines here also change, that is, some of those ads nodes, agents are not able to detect. In this case here, let's stop here. In this case here, just those 3 nodes are able to detect the target. But as you can see, all nodes are agreeing on the network, on the target location. Those particles here, they are getting closer to each other. The clouds, the particle clouds, they are getting very close to each other. But at some point, I think this node will be disconnected. They will be totally disconnected from the remaining nodes. And as you can see, this node is not able to detect the target. Let's see what happens. Okay, I think this time, okay. Too late. Sorry. Not too late. Too late. Sorry. I think at this point here, okay. At this point here, you can see that this node is disconnected. So this guy here is not able to collaborate with the remaining nodes to track the target, and it is not able even to detect the target. So the estimate, the particles representing the target state, the target location at this network location here, at this node, are getting far. They are spreading, since this guy is just extrapolating the target's position. Okay? Let's proceed. But as it gets reconnected to the network nodes, to the remaining network nodes, the red particles, they get closer again. They kind of reach a weak consensus. It's not a consensus. The representation that each network location is different for the target, but they kind of reach a consensus on where the target is. Okay, so this is our demonstration. Let's get back to the presentation. Skip a lot of slides. Okay, yeah, a lot of equations, right? Good. So let's see here the main takeaways from this course. First of all, factor graphs, they are, as far as I can see, as our research group see, this is the best approach to model a distributed inference task, a decentralized inference task, since it captures the network nature, the distributed nature of the problem. So that's a very nice approach. And the belief propagation, it kinds of is a systematic way to design those messages and perform inference over factor graphs. So it is, once you have properly modeled your graph, the signal model, expressed your signal model into a factor graph, it is very mechanical. Designing those messages, it is very mechanical. If you're systematically write down all messages, doing a lot of math, okay? And as you have shown here, this framework is able to handle practical problems. At least you have shown that you can design your message passing scheme to reduce the communication, which is good for real-world applications. The bandwidth is usually a very concern in real-world applications. But still, the local processing, those methods require some local processing capacity to be able to run, since you keep switching between GMM approximations and Monte Carlo approximation. So we need some processing capacity at each network location to be able to run those methods. But in this kind of scenario, you're talking about multiple aircraft. So it is feasible, it's reasonable to consider that you have some processing capacity at each network location. It's not that unrealistic to consider that. Okay? So thank you very much for your attention. Those are my emails. So if you have any questions, please forward to my emails. Okay, it's open to questions. Thank you very much again for your attention.
Thank you, Steven. Do we have any questions? Just raise your hand, please.
Hi, Steven. Congratulations for your brilliant explanation, as usual.
Thank you very much.
I have questions on the practical approach. Well, as far as I understood, the only measurements are from the relative distance between the parties, the planes, and the terrain elevation, and it's in some situations like over the sea or like over deserts that has a different, very changeable terrain. It doesn't work properly. And the other questions, just another question. If you have a situation that your GNSS is denied, probably because a jammed, you are being jammed. So the communication between the nodes don't you think it can be also denied?
Jammed, yeah, I agree on that. So let's start with the last question. Those methods rely on communication, inter-node communication to do belief propagation and to estimate, to do cooperation, cooperative inference task. So if you do not have access to a communication infrastructure, if you're denied, so you won't be able to run those methods. That's true. That's a concern with the cooperative approach. Regarding the first question, actually, those results, those results here show that even though some of the aircraft are flying over the ocean or perhaps are flying over a lake, they are still be able to localize themselves as far as some of the other aircraft are able to localize, are able to measure the ground clearance. That's the meaning of those results here. So those aircraft, just 4 of them are able to measure the ground clearance, but still all of them, after some converging time here, they are able to localize properly themselves, okay? And there are one really important comment here. There are no anchor nodes. They are not relying on an agent, a cooperative, a natural location with a no location, okay, as a reference point to localize themselves. So there's no anchor nodes. They are cooperating, and even though some of them are not able to perform 10, all of them are able to localize, okay? Yeah, but if they don't have information from the terrain, there's no deal. We won't be able to cooperate. All of them will get lost. So if they're all flying over the ocean, you need another source of global positioning to be able to cooperate and properly localize. You'll be able to tell, okay, how far we are from your friends, your neighbor nodes, but not able to tell where your location, global location, okay?
regarding to the first, if your first answer, if you have not, if you are German and you can communicate to each other, do you think this the solution is reduced to several particle filters operating separately?
Exactly. They will run if they are alone and they got disconnected. So they will rely only on local information to do global localization and also target tracking, as I have showed later. Okay, so that's the limitation of those methods.
Thanks a lot.
Thank you. Welcome.
Thank you. Congratulations for your work.
Thank you.
You showed us a scenario where one aircraft drops out of the operation, for example.
Yeah.
I was wondering if the reverse scenario, what will happen in the reverse scenario if one or more aircrafts joined the operation? Is this possible? Is this a case?
Yes, it is. It is actually happening here. So this guy is here, got disconnected. So sorry, I'm not that fast. Here, this guy here gets disconnected. So his location, its location, and the location, it has some particles here representing the target. Okay, so each natural location has a different cloud, a set of weighted particles representing the targets. And they are all stacked together here in different colors to represent the target. This guy is disconnected. And as I show here, okay, after playing here, they will get reconnected, and then the magic happens. The particles get closer to the remaining nodes. Let's see here.
What if we had other aircrafts that were not in here, not in this image?
Yeah, as we're handling here dynamic graph, the number of aircraft can increase. It is fine to increase. Here, there's just 11 aircraft cooperating and 1 aircraft here lost, okay? And then as I run here, this guy gets reconnected and start cooperating. So it is scalable.
Scalable. Could it be N aircrafts?
Yeah, the cost will be higher, but
hypothetically
can be scalable. With a dynamic graph, could be better. Look, our cooperation approach does not involve multiple iterations over the entire network to reach consensus. That's another approach. So in terms of scale, if it is scalable, I think it is, in the sense that another aircraft here, it just increased the number of communications, masses exchanged in its vicinity. The other nodes, one will be aware at the first moment of its presence. As this new aircraft joins the network and start cooperating, the information collected by these aircraft will be spread over several timestamps over time to the remote locations. So it is scalable in the sense that there's no further communication besides this local communication here in the vicinity of each network location as you add another participant. Okay?
Thank you.
Welcome.
Do you have more questions?
Thanks for the presentation. And my question is related to Natasha's question. How does this method handle an adversarial collaborator, like some agent sending wrong signals to somehow.
That's an interesting question. We haven't considered this this attack. It's a kind of attack, I think. Those guys here are cooperative, and they are friends. Okay, they are properly designed to cooperate. And usually in a military application, you make sure that only friend participants can join this network. So you must take care to not allow an enemy to join this network and start jamming, spoofing somehow this process, okay? But if someone here starts spreading wrong information, I believe that for sure the results will get worse and worse, okay? So you must prevent this guy to join the network. That's the point. So use some cryptography, some communication. Your communication infrastructure should be reliable. That's the point. Okay.
Maybe a suggestion for a nice future paper.
Sure, please.
I have a question related to the elevation map. I don't know if I missed the point, but are you considering uncertainty on the estimates about the elevation?
Sure. It is. That model, it's not here, but the elevation model, it's a measurement, okay? First, you need to take into account your barometric altitude. It's a measurement, and it has an uncertainty. And the ground clearance, it is measured by a radar altimeter, and it has its uncertainty by itself, okay?
I mean, since you mentioned that you interpolate the map, are you also interpolating accordingly? Probably.
I'm interpolating the map to estimate the ground elevation at the current aircraft positioning. Okay, so you need to interpolate the map in that sense to get a nice estimate of the terrain elevation at a given location. But our observation model for that measurement, the ground clearance observation, we take into account the sensor error, you take into account the elevation data error. There's an error here. You always can adjust the noise, okay, the variance, for instance, to take into account your uncertainty regarding that observation, the ground clearance, because it is not a direct observation. We need to take into account the elevation map. Okay, but
related to hardware, have you think already about how to make in fact realization on an aircraft about it?
Not yet, but this software here is a very efficient implementation in C++. It is a framework for factor graph inference on factor graphs. Our student, he's already got his PhD, Alison. He designed and have developed this framework in C++, and it is very efficient. It is able to run all those nodes in real time on an ordinary machine. So it's not that unfeasible. The problem is it's the communication issues. We are asking here a perfect infrastructure, communication infrastructure for simplicity. Our first focus here is to understand the problem and to measure the communication burden. But sure, in a real-world scenario, there are missed messages. The bandwidth is limited. There is latency. So there is a lot of aspects for the communication infrastructure that you are simplifying here, not considering this in this work. Okay.
Do we have any questions? No? So let's thank Steven again.
Thank you.
Thank you, Steven, for such nice and inspiring talk.
Sure. Thank you very much.
Thank you, Aldo. Thank you, Pablo. Thank you, Steven. Guys, with this, we end the last day of this of LaFusion. Tomorrow it's not going to be here. It's going to be at the Autumn Hotel at Copacabana. There will be, at this night, there will be a new link for the streaming. Today was at Peshk's channel, but tomorrow will be at iZif channel. The link will be on the website. So tomorrow it's going to go from 10 o'clock to 7 p.m. So it's going to have a lot of paper sessions. It's going to have a lot of panels. There will be a keynote, and the prizes are going to be tomorrow. There will be some announcements tomorrow too. So please join us remotely, join us on site. There is space, there will be food. So come with us tomorrow. So thank you to all the presenters. Thank you, Steven. Thank you, Rui. Thank you, Claudio. Thank you, Pablo. Thank you, Dr. Gomez. Thank you all for your presentations. Thank you all for your time, for your support. Thank you, everyone. Thanks everyone that was here today. Thank you that was watching this on YouTube. And see you tomorrow, thankfully. Thank you very much. Thanks. Paulo wants to say something? Gente, muito obrigado aí mais uma vez pela presença, obrigado pela participação. Vejo todos vocês amanhã, esperando. Amanhã comida de graça. Então, assim, a gente já pagou o coffee break, então a gente precisa gastar o coffee break, né? Então, amanhã vai ser no Hotel Autumn, vai ser para quem for trabalhar, estar com a gente na Fusion 2025, já é um começo desse processo, para vocês verem como é que vai ser. A gente está negociando algumas coisas, discutindo algumas coisas, fazendo alguns ajustes, e para conversar com vocês, não só na Fusion, mas na continuação do La Fusion ao longo dos próximos